Mhm.
Okay, welcome everybody. Yeah, we use the microphone to make sure people online can also hear as well. It's not really needed here in the room. Yeah, this is our year one workshop of the eScience nD-PointClouds project. We try to show some of the results of the past year that we kind of have as an intermediate. We have a rather full program, and halfway we have a break of half an hour so we can discuss over a coffee, and at the end we have time for more discussion during drinks. And in the program itself, we also have a short discussion with the group together about the next steps, what to do, and also how to work together. Should we have, say, meetings with a larger group more often or not? So this is the schedule of today. So first, Martijn will explain some of our basics, how we try to manage the large volumes of point clouds, and how we try to serve them over the internet to users. And our emphasis is really on being multidimensional. So always 3D from the geometry, but there are typically also additional dimensions like time or level of detail, or maybe other dimensions. Then all the way from Australia, we have online Rod Thompson, who has been working a lot with us on how to select in n dimensions. So we are used to working in 2D, 3D, and we specify a polygon or a circle or a sphere, and we say, give me everything that is overlapping or that is inside this query object. But how can we do that easily in ND? Options are boxes, ND boxes, or spheres, but they are rather limited, hyperspheres, hyperboxes. And Rod will try to show that convex polytopes are quite simple to specify, but also powerful in expression. You can select rather well, and also efficient to implement in our setting. Then Thijs will, from the eScience Center, will focus on including a level of importance in point clouds and the COPC file format as used also by Poetry, how that can be supported. Then from civil engineering, we have Sander Vos explaining the backgrounds of the coast scan dataset that is there to monitor now for, I think, over a decade, the descent engine on the Dutch coast. That's not a coincidence, because right after him, Vitali will continue with the same data set and explain what he has been doing to clean the data, and also to figure out what are the deformations and what are the mainly what are the methods to compute deformations. Then we have this break, half an hour, drink together. It's good to know that a lot of the work we are doing is inspired also by education, by student thesis projects, where initial ideas are sometimes born. So our research is inspired by that, and the other way around, our research is also a context for the master students and also projects, thesis, synthesis project, to work in. So students see, actual research project. So it is really a nice, rich portfolio with many topics by students. Too much to mention all, but Edward will give an overview and highlight some of the nice results. Then from Austria, Markus Schutz will give a presentation on his latest work on GPU accelerated level detail generation for point cloud, so also close to the things we are doing. Markus has also been trying to work with continuous level of detail to avoid the density jumps in visualization. Then Nauman from the eScience Center will explain what he did with the point cloud processing on our Delft Blue supercomputer, which is a very nice facility. But how does it go in practice? How easy it is to use? What are the limitations? Supercomputer sounds nice, but okay, how do we get the data there? How can we run our jobs, and how do we get back the results? Then from Esri, we have a nice presentation on the latest development in working with point clouds in the Esri software stack. And I will wrap up with our plans for the second year, a bit reflecting on what we have been doing so far, but what are the next steps? Maybe good to remember that we have a 3-year project. Okay, I will now, by the way, I'm recording this on Zoom, so for our future archive or people that could not be here because we had to move from last Wednesday to Monday due to circumstances, and some people could not attend, but then they can watch it back if they want or fast forward it on Zoom. I hope you don't mind. No, then I'll continue. Then I would like to ask Martijn to start with his presentation. Let's switch the screens, maybe. Prefer that headset. Let's. Okay.
Let's see, does it work? Can you hear me quite nicely? Yeah, great. But the screen is not yet, at least the beamer not. So what is going wrong there? No, but maybe
You could switch.
there is a, let's see if it fixes. HDMI presentation.
Look. After the switch.
Is it things of the graphics? This one. Hier aan het scherm gaan. Always nice technology.
Yeah.
Can I otherwise fire up my laptop?
Yeah, maybe wise. I try to fiddle, but no.
But then you should go on Zoom then.
Ah, yeah. That does the theme. Yeah,
Yeah,
that works.
that's-
So then let's go.
I've got the image here in Australia.
Yeah, that's not the problem. The problem is
Yeah.
here in the room. For a very strange reason, it stopped when switching between the two presentations.
Right.
I'll stop sharing. Yeah, that works.
Yeah, that's great. Zoom. No. Okay, right. Also for the participants on Zoom, is it visible? What you were talking clear?
I can just there. I can.
I think we can, yeah, it works. So, okay, well, after this introduction of the whole project, it's my pleasure to give the first talk of today about storing SFC-based point clouds. And to the point clouds, we add this continuous level of importance. And then I'm going to explain to you how this could be done, offering access on the web to the points in our organization. So Peter already explained a little bit about this. You see that there's more and more points being collected. Really a rapid increase, high resolution scanning devices. And all these sources also come with different kind of properties. So if you look at LiDAR point clouds, they come with XYZ, but also intensity, return numbers. If you look at photogrammetry, then there might be quality attributes added to each and any point. How many photographs did collect or was the point visible on? And for many applications, the different dimensions that you want to query is really application dependent. So change detection might need this additional dimension of time. Segmentation might need classification or normals. Other applications might need this accuracy of the points. So it might also be a nice, nice to have to organize all this information in a higher dimensional set of points. And this is where the term ND comes from in our project, making multi-dimensional points. And based on these multi-dimensional attributes or properties, or how you would call them, putting them all together for the particular application of the user. And when we started this project, a PhD student was just finished, Cheng Liu. I think he was also on the Zoom. And he basically started investigating this idea of having ND points. And the points are then stored inside the database, and retrieving them can be done by means of following this idea of the space filling curve. And we'll get to that over the course of the presentation. But the space filling curve basically allows you to map n-dimensional numeric attributes to a one-dimensional attribute without loss of information. So, and you can also go back. But having one-dimensional values inside a computer is nice because computer memory is still one-dimensional. So the objective of what we wanted to do in this particular bit of research, which we did at the beginning of the project, is to investigate whether our nD-PointCloud data structure could also be used to disseminate points to already current state-of-the-art point cloud web visualization applications. So without altering these applications, can we still serve our data to these applications? And then that looks a little bit like this. We have applications like Poetry and Cesium, globe applications that all can display points. And then on the other hand, we have our nD-points that we store in a database, and we do that in a sorted way. We use the space filling curve, but then we want to connect to this database, and the applications on the left-hand side at this moment do not really understand how to retrieve the data from that. So what we did in this research is that we basically developed a component in between that is running as a web service, which knows how to retrieve the data from our nD-points table. And for that, we also need to add some additional information to make that work. But then basically, within the research, we showed that it was possible to then retrieve this information. So what did we do during the research? We basically took as an experiment some HN3 files. We loaded this into the nD-PointCloud data structure in our database. We then had to make a virtual octree because our nD-PointCloud data structure doesn't have the concept of octree right away, so we had to add it. And then using this web service that we developed, then we could use the Poetry as a visualization client. And afterwards, we could then start to look at, okay, how long does it take to construct this whole set of data structures in the database? How long does it take to construct the virtual octree? How long does it take to retrieve the data from the server side to the client? How huge is the space consumption, for example? So before we go into a little bit more details about the results, I want to show a little bit what is running behind this nD-PointCloud data structure that I was talking about and the space filling curves. So I'm not sure how many of you are already familiar with space filling curves. Maybe here at the beginning, yes. Well, as I said, a space filling curve is basically a mathematical curve that runs through we could say through a grid, and it touches each and any grid cell only once. And here you see on the slide one of these curves, which is the Morton curve, and you can construct it as follows. You go with multi-dimensional data as input, so that's along the axis, and you then arrive at a one-dimensional value. So how does that work? So along the axis, we have integer coordinates, 0 to 7, 0 to 7 in the y dimension. And then what we can do, for example, for this point 4, 5, we can look at what are the coordinates of these points, of this particular point. We can look at it in binary. And then we can do bitwise interleave of the coordinates. So we basically take the y bit at the first location in the y value, and we put it in the new number. Then we take the y bit in the x coordinate, and we put it in the new number, and this then repeats. So you can also see it as some sort of matrix that you transpose. That's another way to look at it. But basically, this new number here now encodes the information from both the x and the y coordinates, and we haven't lost any information. The only thing that we need to do is to transform to integer coordinates. So that is possibly a step that we do in front of this. Then what is nice of this, and you can see that also here on the slide, The coordinates are 2 in the beginning, and each coordinate has 3 bits to describe it. You could also look at it at the version in the what we call the key, so the transposed version, and then you have 3 groups of 2 bits each, and the first group in this number basically also indicates where the original point is in this whole space if you subdivide it into quadrants. And it's then an indication in which quadrant does this point occur. So this point 49 is indicated, is located in quadrant number 3, and we can see that from the 2 first bits of the SFC key. And the nice property here is that this also generalizes to higher dimensions. So it also indicates in 3 dimensions in which of the octants, for example, a point will reside, or in 4 dimensions in which of the 16 subparts the point will reside. And this then is also a recursive property. So we can add 2 more bits to the address in the key, so 3, 0, and then it indicates first you have to go to the upper right quadrant and then to the lower left quadrant, number 0. And you can repeat this again, indicating that this point 49 is then at the 1st quadrant repeating. And what I wanted to show here as well is that all these points that have a similar curve key, so from 48 to 63 in this case, they all start with the same 2 bits. So it's also an indication that these curves, if you sort points along them, they will put the same kind of point that is in the same kind of region, in the same kind of location on the curve. So you also get some clustering somehow for free if you do a sorting of your points along this curve. Then how to query? Because we basically go from this n-dimensional inputs to the coordinates, 3D coordinates, 4D coordinates, to this 1-dimensional value. Then we only have the 1-dimensional value. So how would you then query? You still have an application that somehow knows the space, which points you want to retrieve. So for example, in this case, you want to retrieve the points that are all in the blue box. But in our table, we have only these 1-dimensional values. But because there is this property of the space filling curve that it's that you can go for the first 2 bits is corresponding with the top quadrant right. In the previous example, you can also exploit that property while querying. So you can find basically, okay, let's see if we have our whole curve that will definitely overlap with this blue box, right? So we can say, okay, if we want to look for points that are in this blocks, then we need to see between the value 0 and 63. Between there, if we find points in our database, we have an answer to our question that we will have points. But we will overfetch, right? Because we will also fetch parts that are not there. So we can basically use then a subdivision. In this case, it's a 2-dimensional example. So we can split the curve into 4 parts. And each part of the curve also corresponds exactly with a square box. So we can then check these square boxes with our query geometry. And the square boxes also happen to correspond with a range on the space filling curve. So in this case, we can know that the ranges that will appear here are basically these 2 parts on the curve. So 16 to 32, and 32 is excluded, so up to 31 included. And then from 48 to 63. And we can repeat this process again. We can refine these boxes of the NRE tree or the plot tree that it basically corresponds with. And then we can see, okay, which parts of the curve do we need to consider for points, to look for points. And we can repeat this process until we have a very good approximation of our query geometry. But we could also stop halfway and accept that we will overfetch a little bit points. So we have some way to say, okay, how well should we approximate our query geometry with this approach? And I think Rod will also explain that you can model the query geometry as any convex polytopes. And then you can also go inside this tree and do the tree traversal there. Making efficient use of box versus any convex polytope predicate. Okay, so that's the querying part. Then a little bit about the continuous level of importance, CLOI values. Because if you look at data that is collected with a laser scanner or from photogrammetry, there's not directly level of detail mechanism inside the collected points. And you see many people that are doing level of detail of points is that they store them as fixed levels. And the first level then doesn't have so many points. The level next to that has twice as many points or 4 times as many points, depending a bit on the type of dimensions that you're working with. And from this, you can also go to a description that is continuous. So each time, inspired by this level organization thinking, you add to each and any point a specific floating point value. And you make sure that the floating point values that you add are distributed in the same sense as this level organization thinking. So you don't have so many overview points, having a value close to 0, for example, and you have super many points that will have a value of 4 or 8. And then make some sort of curve like this, that it will have a distribution like that. And this value then can be generated quite efficiently and cheaply by just throwing a dice, running a random generator, and running it through this formula on the bottom of the page. And then you will have an extra attribute value into your points, extra value, on which you can decide which of these points should we show for the overview and which of the points should we show when you are getting very close to the surface while moving this virtual camera in your virtual world. So that as a background, now back to the organization of this whole database. How can we go from our input to our database? So we do that with the following steps. We read the last files, and from that we read the X and Y and the Z. And based on this X, Y, and Z, and the CLOI that we have to add to each and any point, we can basically compute this space filling curves. And we do the bitwise interleaving for these dimensions. And the additional attributes, we put them just as normal attributes in a record in the database, just as additional columns. And then we load the SFC key and the attributes together into a table into the database. And then we have to do a sorting step for so that all the points basically will follow the sort order along this space filling curve. And inside Postgres, you can do that as follows. You can make a B-tree index on top of the database table, indicating that there is this SFC key and that it needs to be indexed. And once you've done that, you can also say to Postgres cluster the table on top of this index, which basically will reorder, reshuffle the records inside the database. And then you will have a sorted table. And then at the end of this process, what we also do is that we record for the, and that's basically to make the querying process a little bit more efficient. I didn't tell anything about that so up to now, but basically here you can see this, right? If you know already that in your database that in certain parts of your domain there will be no points, then it's good to record this kind of information. So we keep basically a histogram. And if you want to see more about that, you can go to I can see this. We keep a count of how many points are in each of these quadrants. So in this case, everywhere there's points, but in a regular scan, you will have some parts where the domain will be rather empty, and in other parts it will have a lot of points. So we keep this up to a certain level in this tree structure, how many points there will be. And that's what we call the histogram. Basically saying, okay, here there lives a lot of data, and here there's not so many points. So using this histogram, you can then do this querying step even a little bit more efficiently, guiding you where there is data. Okay, so that's the last step when we have to make the data structure, creating this histogram. Now a bit more about this this web service component and how am I doing time-wise. Should speed up a little bit, maybe, right? This PC serve component is basically there to support O3 and Cesium to be able to access the points in our SFC-based organization, but it somehow expects to find groups of points which are really organized as an octree server side. So we thought about two options. We can either adapt O3 or Cesium and make it aware of our nD-PointCloud structure, or we can basically model an octree on top of our nD-PointCloud structure, and then use PC-serve to make like the queries directly to our nD-PointCloud structure in the database. So we have used this option, making PC-serve basically acting as some sort of octree proxy to our data structure. And then we need to carry out an additional step after creating the point cloud table, the nD-PointCloud table in our database based on the space filling curve keys. We need to do create the layout of the octree. And this is basically querying where does the data reside in the nD-PointCloud data table. So basically, given this point cloud table that is we have in the database, we then can make this virtual octree table. And we use our own query mechanism to determine if a particular octree node has some points, and if it has points, then we store this as an octree node. And if we have found the octree node, we can basically refine it into its 8 children. And with this additional property that we added into our table with the points, so for each and any point, we added the CLOI value. We know that all the points that have a CLOI value between 0 and 1, these need to go in the root node of the octree. And if we have split the root node once into its 8 children, and we retrieve for these nodes only the points with CLOI value between 1 and 2. And this then repeats and repeats until we know that there will be no more CLOI values, because we hand them out up to a certain maximum, like 7 or 8. So then the whole step of preparing before we can use the PC-serve looks a little bit like this. We start with the last file, we add the SFC keys, we do the sorting, we create our histogram, and then we make an octree table by querying our nD-PointCloud structure. And this octree structure can subsequently be retrieved from the octree table, and the point data can be retrieved from our SFC-based table using the ranges that we store for each and every octree node. And then PC-Serve can also determine what is the serialization format. So Poultry expects, for example, LAS files. So it can serialize as LAS file, but Poultry, the newest version, also has its own format. So we can also supply Poultry with its newer format, with its own binary format. So that's like an option that you then have. So then some results. This processing takes a bit of time. In this case, we took the two last tiles, which were like 3 GB of input. And then you can see that in Postgres, it's not especially space efficient. So that is a point of attention. Did a factor of 25 in space consumption, but this is mainly due to Postgres storing everything as records. And on each and any record, you also store some transaction overhead, like accounting when is the record inserted, should we roll it back? So that is expensive. So that is something to be investigated further. The octree construction was basically taking 1 hour, so not too bad, I would say. And then if you have this octree table, you can also derive some statistics from it. So you can see how many nodes will you get and how many points are on average on a specific level. And then while using Poultry in the interaction, you can also see how long does it take to retrieve the data for one particular node. And this then is between 450 and 600 milliseconds, which is not particular super fast, but it is in interactive rate. So if you start to browse around, you can supply the data reasonably fast enough so that users can directly start to interact with it. And then I have a small demo that basically recorded it as a screencast. Here you see the client, which is Poultry. It's not running yet. On the top right, you see the PC-Serve component, and it's not started. So let's start the PC-Serve component. You see that it connects to the database because the database then has a little bit more queries running. And then when PC-Serve is instructed to fetch some data from the client, you see that the client sends the requests, they end up at PC-Serve. PC-Serve connects to the database, and the database then does this querying of the ranges for the points. So then the data is shipped from the database back to PC-Serve. PC-Serve makes sure that it arrives to the client in the right format, and then the browser basically does the rest. And then Marcus knows much better how that works than me. But basically it loads the points into the GPU memory, and then you can display them. And a little bit later today, I think Thijs will also mention something about CLOI and how this CLOI value will be used exactly within the client to be able to visualize. Because this CLOI value can also be shipped back to the client. And this is also what we do. Let's stop the video now. So yeah, some conclusions. We presented the nD-PointCloud structure and also the PC-Serve component, which is really acting as a proxy to our SFC-based point cloud organization. And in this sense, PC-Serve is also a case of dog fooding because we use it to query our database all the time. So in a way, it's also showing that we can do efficient queries with the point cloud data structure in the back. And we have used the Poultry renderer for this interactive visualization. So what we are currently working on, and some of the aspects we'll get back to in the program today, that is parallel pre-processing, because we saw that there was quite some time in setting up the whole database. some parts can reasonably efficiently be done in parallel, which would at least reduce the amount of time that the user has to wait before the process is finished. Another important aspect is the disk size consumption in Postgres. So we're currently also looking at alternatives for that. And one of the alternatives we see is that Apache Parquet files seem to be promising, but they do reside outside the database. So how can we then still make a connection with these files? Another topic that we would like to work on is supporting more clients, not only Poetry, but also Cesium and maybe even QGIS. COPC could be an option. But then you run also into the issue that you need to think a bit more about coordinate systems, coordinate reference systems, because Cesium has its own coordinate reference system, and it's not directly the AHM coordinate reference system, so you have to do a transformation. I told you that PC Serve was like option 2, right? We didn't change anything into Poetry, but we could also change Poetry to understand our SFC-based sorted table on the web server. And then maybe it's even more efficient to retrieve data in that way, making bigger blocks, something like that. Not exactly sure yet how that needs to be done, but that's another thing that we're investigating. And then Thijs will tell you something about the CLOI inside the renderer. And Vitaly will tell you something about this kind of principle, but then with other dimensions, not only X, Y, Z, and CLOI, but also considering the time dimension or even multiple time dimensions. So with that, I'd like to open the floor for questions. Thanks for your attention.
Thanks for explaining all the details and the fundamentals of our project. We have not so much time for questions, but 1 or 2 questions should be possible. Maybe for the people online, it's good to use them.
Thank you very much for the presentation. One question: if you would like to continuously add data of some the system that will keep producing, how does the system cope with continuously updating all the histograms, etc. stuff?
Good question. At the moment, we have only worked with these data sets that are fully there at the beginning. So it might be challenging to add new data into it. And I think it boils down to thinking ahead of how much data will it be and how much data do you want to support in terms of number of bits that you would need in the future also. And we have also had some ideas in splitting somehow this continuous stream of data into a part of the stream that you have already seen and have already captured, and you probably are not going to change that anymore, and the data that will come in the next day. And somehow, maybe this can be exploited in this setting, that you say, okay, we have a very good archive that is really well organized, and once or twice every day, we take like the stream that we have seen, so that is coming in, and we put it into our final archive somehow. But I think with the sorting, this would require that you would need to resort some parts of the data, or even very many parts. But that depends a little bit on how you set up this space filling curve and the thing. So there's also definitely interesting research questions to be found there.
This was a simple question, but not an easy answer. Last question, if any, otherwise we quickly move on to the next presentation, maybe online to people. So,
If not, okay, then Martijn, thanks a lot, and let's quickly move on to the next presentation, and let's see what is the best way. Martijn, can we use your screen to show it here in the room? And the next presentation will be by Rod Thompson, and Rod can share screen, and then it should show up over here, I hope. Rod, can you try to share your screen?
Yes. Is that working? Oh,
Yeah. We see you now on the screen, but somehow we cannot hear you that well. So
oh, okay.
maybe
I'm muted now. Is that working?
I think it is working. Yeah, we see the edit mode here at the moment. Maybe I should.
How's that? Is that working?
Yeah, it looks good.
Right. Okay.
Can you say something, Rod?
Yes. Is that all working properly? Can you hear me now?
Yeah, I'm playing with the sound.
Oh, right. I'll keep talking then. Yes. Can you see the mouse on the screen as well? Is that visible?
The mouse is visible, yeah.
Yes. Okay.
Okay, I think this is the best way. So I put the microphone near the laptop and hope we can hear you. Yeah.
All right. Is that loud enough? Is that clear?
I think so,
that-
yeah.
Okay. Well, good morning, everybody, or afternoon, or night, or whatever. I'm a bit confused. But yes, thanks, Martijn, as well. That's a very good introduction to what I wanted to talk about. Why would we use a convex polytope? The reason is that it's more selective than a minimum bounding hyperrectangle, but it's not a fully general one. So why not go the whole hog and go straight to a fully generic region? Well, it tends to be very slow, whereas a convex polygon can be very much faster. And it's useful. There are cases where a convex polytope turns up in more than three-dimensional point clouds, and the most classic case is the 3D view frustum. You can see in the left image here, it's the region that we want to look at in a 3D view is a convex region, so it's not a problem there. And when you're looking at it in the classic example of XYZ and CLOI, the continuous level of information, it still is a convex region. It's just that in this case, you want more detail close to the viewpoint and less as you get further away. So it's a kind of extension of a tetrahedron, except that there's a Z coordinate in there somewhere as well, but I can't draw 4D very well at all, so I've just dodged that around. Why is it quick? Well, because a convex region you can represent as a series of half spaces, and I'll go into a little bit more detail on this. I can't draw infinite half spaces because they fill the whole screen and you just don't see anything apart from one color screen. So these are all shown as if they will stop, as if they're all finite planes. But a region such as this can be represented as just intersecting half spaces. And a half space we define as a vector and a scalar, where this omega is a unit vector and beta is a scalar. It turns out that beta is the distance to the origin of the half space. And it gives us a very simple test of whether a point's within a half space. The exterior of the half space is any point where omega times x, now that's a vector product of the omega that defines the half space and the coordinates of the vector of the point. So we simply make this calculation. If it's greater than 0, we're on the outside. If it's less than 0, we're on the inside. And if it's actually equal to 0, we're right on the hyperplane that separates them. Now, to calculate that is a very simple order n, where n's the dimensionality of the space. So that's a very quick calculation in itself. And when we come to our convex polytope, the question is the point within the convex polytope, which is a region defined by H half spaces. I've just used the term H, the letter H for that. We just have to test it against each of these half spaces. And so that's an order NH operation. So just to find a point, is a point inside a convex polygon is just simply order NH. Now, going back to Martin's search algorithm, this red line I've put in here is defining a convex polytope, and those individual straight lines are the half spaces. If a region such as this, which as Martin explained, is a maps to a simple range of keys, if this is outside any one half space, you can forget it. We don't need to look at that again. On the other hand, if one of these regions is within all of the half space, and not just one, but all of them, then we can use that range. That range can just go as is. We don't need to break down that index node at all. So that can basically be published effectively. It's only here where that doesn't, neither of those apply. We have index boxes that we have to process further, and we have to subdivide them, as Martin explained. So the other thing is, it's not just all the points in an index we have to test. If all the corners of an index are on the outside, we can discard the index box. And if all the corners are within all half spaces, we can use the box. But we can actually, that means we only need to test 2 to the n points. We don't need to test all points in the index, of course. But we can do better than that. We don't only just have to test 2 to the n points. We don't have to test every corner of that index. What we can do is what Hai-Cheng referred to as the scan algorithm. Just assume our index is centered on a point x, x1, x2, x3, then we can describe the whole index box by the size of it in terms of the, I've used delta 1, delta 2, and delta 3 because this index box doesn't necessarily have to be square. Delta, you know, the size in the x direction doesn't have to be the size in the y direction, and doesn't have to be the size in the z. X and y probably will be the same, but the size in the z could be very different. This could be in kilometers and that could be in meters. So the corners, these individual corners, are defined as x1 plus delta 1 plus or minus delta 1, that's 2 corners. x2 plus or minus delta 2, that's 2 corners. And x3 plus or minus delta 3, that's 2 corners. So you finish up with 2 to the n corners. If you do that, with a half space and the point centered, what we can define in relation to the half one, and this is important because it's only in relation to one half space, you can define two specific corners of the index box, hypercube if you prefer, where C plus is the one that steps in the direction given by the sign of omega. Remember, omega is the vector of the half space, whereas C minus is the one that steps in the opposite direction to the sign of omega. You can fairly easily prove by this definition, with D plus is effectively the distance between C plus and the half space, and D minus is between C minus and the half space. You can prove fairly easily that D plus is greater than D minus because you add it each time. And for the other corner, and for any other corner, that the distance to D plus is greater than or equal to the distance to any other corner, which is greater than or equal to the distance to D minus. So the corner, we had a little bit of trouble in our nomenclature here, talking about the nearest corner and the most distant corner, because really all you can say is the C plus is the one most likely to be outside the half space, while C minus is the one most likely to be inside the half space. Just looking at this in pictorially, we've defined, and again, unfortunately, it's got to be drawn in 2D, but it could be 4D or whatever. C minus is the one most likely to be inside, and if it's outside, then the whole of A is outside. In the case of B, C plus is the most likely to be outside. So if it's inside, then the whole of B is inside. And if they're split, then we know that C cuts the boundary. So that's a very quick operation, because calculating C plus and C minus is an order n operation. You know, you just go once through each dimension. Calculating whether C plus is inside and whether C minus is inside, that's also order n. So for every node and for each half space, everything is order n. So the complexity is only the order of the number of half spaces by the number of the dimension times the number of index boxes you've got to search. So it's very much polynomial. So applying that to an actual convex polytope, this blue figure here is a convex polytope. When you apply it to different index nodes, you'll see that N1 fails the test. It's on the outside of H2, so it can be thrown away straight away. Test H1, it splits it. Test H2, it's on the outside, so reject it. When we come to N2, it's inside H1, it's inside H2, inside H3, and inside H4, so we accept it. N3, it's inside H1, inside H2, inside H3, but not inside H4, so it gets put into the too hard basket for the moment. And the same with N4. It doesn't fall within H1, and it also doesn't fall within H4, so it gets put in the too hard basket. Then the next step is the ones that are in red that have gone into the, then they have to be refined and split into 4. And you'll see now that N3 gets divided into 3 that are still on the edge, and N34 is now completely outside, so it can be eliminated. And in the case of this one, N4, 3 of those can be rejected, and N42 goes on to the next level. And when we look at the the next subdivision, you'll see that we finish up with 3 of these from N3 that are inside, and what's that? 4 of them. Is it? Sorry, there are 4 inside, 6 on the edge, and 2 on the outside. We can be rejected, but the whole of N4 now has been rejected because none of these. Well, you can see that N421 is outside H1, but N422 is outside H4. We have got a situation here with one that we picked up early, N4, which we've eliminated, but we've had to take it right down 3 levels of the index to do it. So that doesn't really cause too much trouble because the problem gets eliminated. And so we don't actually go to the database with ranges to do a search, but it does slow things down a bit. And so we started looking at this concept of guard half spaces. This happens wherever you've got corners like this, where the corner is fairly acute. So the idea of it was, when we look at a case like this, if we could put a line, a half space through there, it wouldn't affect the number of points we want to include, but it would eliminate N4. So if we put at each corner these guard half spaces, then we could eliminate N4 and anything like that. We could eliminate anything down here or anything that hits this corner. And this down in the left corner, it's a little hard to interpret, but this is an actual view frustum. And these points here are the corners of the index boxes that have been searched. And you can see that even though we're looking in this direction here, there are a whole lot of boxes over here that we've searched and then found we don't really need. And that's because these lines cross out here as well. So if we throw in another half space there, we'd eliminate all those right from the start. So it may be worthwhile, and this is, you know, subject to more investigation. I think there are no more than 2 to the n guards for the whole convex region, and that we need n-1 guards for any individual edge if it's too sharp. Issues though are it gets complicated to understand for n greater than 3. It's really easy to understand in 2D, and it adds half spaces to the definition, which might slow the extraction more than you gain by eliminating these N4s. So research is needed. Now, the other thing is non-convex regions. There are 2 ways to get around them if we could still use the method for non-convex region. We can make them up by adding together nearly there. We can either add convex regions to make up the non-convex, or we can take a convex region and subtract one. The complexity now is it adds this the number of convex regions to this complexity. There's a strange thing with this, and I won't go into this, but it turns out that you're better off making things overlap as much as possible for improved. So the open questions: how effective are guard half spaces? How effective is splitting a non-convex region into convex subregions, and how to split them? Is there any algorithm to decide which is the best way to do something, and how to use additive and subtractive splitting most effectively? They're, as far as I can see, they're all questions that need to be considered. So any questions on that?
Thank you much for explaining how we can also query very fine point clouds now. So any questions? And again, we are also now running out of time. Online. Just open your microphone. Okay, it does not seem to be the case. So, Rod, I think for sure we have lots of topics to be further explored. Thanks a lot for staying up so late in Australia.
Okay, yeah.
Thank you very much. We now move on to next speaker. Thijs will explain how to include CLOI and produce the poetry file format. What I want to do, use your screen to display.
If that is.
Yeah, I think that works quite well.
That is working at this moment. It was. This.
Yeah, good. Starting to zoom. Actually, be better if I share screen from my laptop because I also want to do a demo.
Do you have Zoom open or something?
Yes.
Do you have a converter that needs to be connected? Is it this one?
Yeah. Right. Okay, so I'm Thijs van Amstel from the Netherlands eScience Center, representing a part of our contribution to this project. From a large point of view, we're looking into actually putting these new features of point clouds into practice in several different ways. One of the ways is the additional features on a large data set, so AHN in practice. And after the break, Nauman will give a detailed presentation on that. Instead, I'll be looking into how to apply these levels of importance in a viewer, in poetry in specific, and also looking at file format options, because we've noticed that the database format is very versatile. Database format that Martijn presented, but it also has its limitations specifically in storage space, because it takes up a lot of space. So I'll go into a couple of options that we're exploring there. But starting off, starting off with a short description of the continuous level of detail, which Martijn already touched on. So this is kind of a discrete level of detail like an octree, but then subdivided along the same probability density curve to make it continuous. And for the center image, I've kind of bashed poetry into submission to be able to show you the blockiness that you can get from loading points and then displaying them based on a discrete subdivision like an octree. So poetry has very nice capabilities of hiding this kind of stuff. So normally you don't see that. You have to really try to make it do stuff it doesn't want to actually show that there's blockiness in there. But you can see from the image that the nearer the view, a lot more points are loaded in than further away. And the transitions from having a lot of points to having fewer and fewer points are very abrupt and very discrete. So they're not square in nature. And especially if you have visualizations like this, where we show the points individually and not scaled based on nearby points, then you can see that blockiness, it can become very disruptive to the experience. So we want to try to remove and reduce this kind of discrete step of many points to stepping all the way to all of a sudden having few points. But this doesn't only apply to visualization, which in this case, but it can also apply to processing, where you might want to start processing a few points, and then keep adding more and more points to the process, and focusing on kind of overview first and then detail second. So there, the order of importance can also be important. So with an octree, you can have the root node processed first, and then moving into the childs of the root, and then the children of those, and moving forward. But with a continuous level of importance, you can have a more granular scale for granular approach. So we've implemented a proof of concept into Poetry to use the continuous level of importance. Or maybe I should describe here a little bit more that the level of importance, the continuous level of importance, as Martijn described, can be generated based on a semi-random generator, semi-random number generator, but then it's not uniform. It's this logarithmic curve where there's only a few points with importance near 0, and a lot of points with importance near 1, or usually we scale it up to something similar to the number of octree levels that we have in the data. So for example, if you have 8 octree levels, then we also go up to importance level 8, but that's just scaled up linearly after having this non-uniform random distribution. And in the background, we have this level of importance computed offline beforehand, and then added to each point is added this importance value in such a way that it's also distributed nicely over the scene. So it's not that it focuses on one part of the scene. So we've implemented this, and we've adjusted Poetry slightly to show this level of importance, or use this level of importance when visualizing the points, specifically as a filter to points. So we load in a lot of points, and then afterwards we filter out a number of points that don't conform to a threshold setting. And this threshold is based on the level of importance and the distance from the camera. So basically, near the camera, you're allowing more points, and further away from the camera, you're thresholding them to only use points with a low value in this importance way. And so on the top right, I've given an indication of roughly the formula that's behind that. It's used based on importance, the distance, and the threshold value. And the 3 images shown here are kind of the base point cloud with all the points shown, and then the continuous level of integration, levels of importance applied to it with a certain threshold. And here you can kind of see that this gives a result where you have a rough kind of fixed number of points per pixel, instead of a fixed number of points per part of the scene or per depth of the octree that you want to visualize. There you can limit the number of points kind of in a screen coordinate fashion. And then on the right, we've also added a weighting factor to the level of importance. And this is even more of a proof of concept because we're envisioning more for this in the future. Here it's weighted by the class that's also present in the AHN data. The data is classed into 4 different classes for buildings, ground, water, and other in this case. And we've given a higher weight to buildings, so that these basically get a higher importance and are more apparently shown or are filtered out less often. And by the way, in this filtering procedure, we found out that the most effective way of doing that is in the renderer itself. So basically, we go through points. Each point is passed through this formula to see whether it passes the threshold or not. And if it's supposed to be filtered out, then we just render it off screen somewhere. It's the easiest way that we found to actually do this. But moving back to the weighted level of importance. So here it's just the class has a hard weight applied to the importance, but we envision that we actually want points that are salient, that are more descriptive of their local scene to have a higher importance. So there you can imagine that points on a corner of a building or a corner or an edge of a building of a plane could be more important than points in that plane, or a high point on a mountain is more important than points somewhere else on the mountain. So then you would get the important points would get clustered, but they would be clustered in parts of the scene that are more descriptive of the scene. So this is just a proof of concept to kind of see if we can move towards that. So that's the part for adding the importance to poetry, to the visualizer. Second part we've been looking at is file storage options. So Martijn indicated that the database approach in the case he studied took up to 25 times as much storage as the input. And this can actually be a breaking problem when handling massive data sets like AHN, because we don't have that much storage, or we don't want to use that much storage. So we have to also look at file storage as well, which is often a lot more tools towards this specific purpose. And if you look at files like the LSG files, they have very good compression as well. So their compression can be up to factor of 10 or something, which is something that's very difficult to reach in database approaches. And also, if we look at, for example, the proprietary format for poetry, for the new version, there is some compression in there, but it's just not as efficient as the LSG compression, because that's very much tools towards two-dimensional formats. So two formats that are kind of relatively new, but quickly gaining ground in field is the EPT and the COPC format, which stand for the end-to-end point tile format and the cloud optimized point clouds. And they kind of follow from each other. So the COPC is in large part based on the EPT format. So on the left side, I described the EPT format, which is partly metadata, so descriptive description of the scene, of how big the scene is, which part of the world it covers, and how it will be subdivided. Subdivision, by the way, is done in octree format, where it's split hierarchically with a large node center, or covering the whole scene, and then subdividing the scene hierarchically. And then the point clouds themselves, which they call tiles, are stored as LAG files per octree node. So the LAG, you get the benefit of the good compression there, and you can kind of pick and choose which parts of the scene you want to visualize based on the octree and how deep you want to go within certain parts of the scene. So on the bottom left, you actually see the hierarchy file, but it gives an indication of how many points are present in the different cells of the octree of this particular data set. But when applied to online served data, then data transmission becomes an issue, and you quickly notice that a lot of small files is a lot more heavy load on the transition, on the transport, than one big file. So there's a lot of data overhead if you have a lot of small files. And that's where COPC comes in, because the COPC actually has the same organization, but put into a single LSG file. So this has the advantage that any reader that can, or any program application that can access LSG files can read COPC files. It's just that there's some extra information near the back of the file, the COPC variable length records, that describe the organization of the file, such that you can also load in parts of the file. So there, if you have the header and the extra COPC information, then you can quickly access only part of the points that are in that file, and only load those. And this works with the internet protocols that you can also send parts of the file, only access parts of the file, and possibly compress them or put them into a new LSG file that's temporary and only have that part that you want to access. So there you can have one major massive file that you can access specific parts of, And you only have to do a limited number of access operations. So there you really save this transition or this transaction cost. But again, we've noticed a disadvantage or a problem when applied to our case because we have massive data sets, and then having one hugely massive CPC file can be a problem for storage again, because we might have distributed storage, or we might have trouble processing batches that are that big. So there we're looking to do a hybrid approach, where we want to still have large files, but a couple of large files. So a small number of very large files. So we want to cluster parts of the octree into CPC files. It's basically what we're doing. We're keeping the EPT metadata file, and then instead of having a point cloud tile per octree node, we want to cluster a fixed number of levels of the octree together into CPC files. But that's still work in progress, so I can't really show the result there. So conclusions for this talk: we've looked at filtering for visualization by continuous importance in Point Reviewer, and we've looked at several file storage options for huge data such as AHN. So if there are any questions, then you're very welcome to ask them.
Anyone question? Yeah. Hi, thank you for your presentation. I was wondering what exactly the problem is with handling large files. Because as I understand it, the cloud optimized file formats are mainly used for or developed so they can be processed also in the cloud, where that is less of an issue. So what type of problems did you encounter with the one monolith codec file?
So there are two parts to this answer. First off, that we're currently also applying the cloud optimized point cloud file as stored in storage capabilities or storage capacities of the university. So that's not the actual cloud storage, and so it doesn't have the same growing potential as cloud storage could. And secondly, we've also noticed that when processing these files, when producing these files, we run into space limitations of the processor, because there seems that if we go over a certain data size, then the supercomputer can run into trouble. So this is something that probably Naman will touch on later, but basically we want to explore more options than just having the one monolithic file.
Are there more questions in the line? Just open the microphone. Guys, I have a question. Is it for 3D data, or could you also make it more general for ND or so 4D with time or?
Right. So in the whole setup of this project, we've had high dimension as a prerequisite. So it's always kept in mind that we want to expand this to high dimension. But for visualization of high dimensional data, you immediately run into the issue that humans can't see 4D, and the computer can't display 3D even. So the computer is mimicking 3D by very smart hard drive or graphical processes on a 2D space. So if we want to visualize higher dimensional processes or higher dimensional attributes or higher dimensional data, then we have to in some way make this make a conversion from high dimensional to 3D or 2D, so that the visualization engine can show it to us. So these are.
But are the file formats suited to transfer this?
Right. So up to a point. So most of these file formats have LAZ as the actual storage format, and that's bound to the features that are allowed in LAS files. So some features are in there. Other features might require a newer version of LAS to be developed, but that's kind of outside our hands. So some attributes like time is in there. But for example, already for the importance value, we have to add our own records to the loss file, which is possible, but it takes some extra work.
Thanks. Other questions in between? If not, then I would like to ask.
I also almost forgot that I had a demo, which is why I let the actually hooked up my own computer. But so basically what we did with Poetry, which is this viewer, we added a slider where you can slide to reduce or filter out more or less more or fewer points. That's based on the distance to the viewer. So you have roughly the same points per pixel in the end. And we can also apply a weight to this to show, put more or less weight on certain classes within this. So, you're very welcome to talk to me during the break for more demo material. That's what we're here for. Okay, so that's my.
Again, thanks. Let's see how we do with the technology. Because I'm a bit worried that my laptop may not work. Are you connected to the server drive or not?
Yes.
You want maybe, yeah, if Sander's presentation is there with a number on the server drive. I think it's number 4 or 5.
Yeah.
4, yeah.
No, we want to do. Yeah. And probably you want to full screen. Yeah. Not sure why it's full screen.
Maybe, so it's probably that.
That's full screen. But I am, Zoom. Then it's setting it to presentation mode. Should it work now? Okay. 5 is reloading. That's written normally for websites. What does it like? Presentation mode.
Yeah. Try again. Yeah, that's working again.
Thank you very much. This will be a little bit of different kind of presentation because I'm a huge producer of point clouds. So I mainly use the laser scanner to field stuff along the coast. And now what I wanted to show is just a small show what we have done so far. I'm not going to into much detail in each subject because I have many people working on it. Most of the stuff is published in articles. So if you have any questions, you can look up the article or you can ask our people. Just give an overview of the team. We have Mika, Paul, and me, which are 2 PhDs and 1 postdoc. And Roderick and Siert are our supervisors. We are all coastal engineering and geoscience. And just, yeah, this small statistic, this is quite a large project. So we have a lot of people working with us together. And we also have quite a lot of output. So we have some national newspaper articles, television, more than 40 contributions in articles, and about more than 150 references just based on the CoastScan data set. And we also have we shared the data with more than 10 PhDs, and that's still people going to use it in the future. We have been measuring at 3 locations. So what you see here is the laser scanner, which we will just position along the coast, and then we keep it there for half a year, 3 years. And we make a scan each hour of the beach. And the idea is that these are totally new data sets. There are only 2 of these machines in the world. So the data sets are quite special in a way. And we try to get the most accurate data sets possible. So we try to correct as much as possible from the point of view of the instrument. So we have a computer which is programmed, and which will program the scanner every hour, and then we will georeference all the data. So all the data we produce is georeferenced in local coordinates in Belgium or in the Netherlands. And we also do time-dependent corrections, which means that if the laser scanner is shaking a little bit, we will try to correct it for every time step. We have been trying to use different aspects, and we can get it quite accurate. If you're looking at the error per 100 meters, I have an accuracy of about 1 centimeter in a Z per 100 meters, and which is, I think, it is the most accurate you can get, because the instrument itself is always lower. So you use some tricks. I'm not going to. So this is just what we have collected so far. Most times you do one scan per hour. 24 hours a day, and then we have something between 3 to 8 million points per scan. And this is the overview. We did it in 3 locations. As you can see, we have about, I don't know, 45,000 scans with times 8 million points. So that's quite we haven't thought much about how to, we just store the data per hour and per day, and that is. So there's no complicated stuff. I'm learning a lot of stuff here, how to distribute your data, and but in a way, especially on a cluster, it is quite fast, because you can write a routine that will just pick 1 file, and then when you, for example, the Maria Kerkenbad take about 10,000 hours to do the calculations for the computer core hours. And I just write in subroutines in such a way that the file distributes it over the course, and then picks up a list of files, does the results, and then clusters that. So it's maybe a little different approach. What I'm now going to show is a lot of stuff what we have done, just to give you an idea what is done so far, and then you can pick up from there. So, for example, what we are doing on the bottom is the laser scanner. This is part of the beach. So we have about 700 meters by 300 meters of beach, which is changing continuously. We have a part of the dunes, we have a part of the beach, and we have an area which is called the intertidal area, where the sea is coming in and out the whole time. And you can see a little bit of the angles what we are working with. So we also, the laser scanner is quite shallow. It has its advantages and disadvantages. We get also a lot of parameters from the laser scanner. It will, if you look in the data set, it has 8 parameters per point, and we try to store that and distribute it also. So Mika, he's on the photo. He's doing a lot on clustering and detection errors. So this is one of the works where she has been working. On the left, you see the beach. And all the colors represent different clusters. She has been using different, for example, like BB scan, K-means, different clustering techniques. And she's been trying to use different clusters and then see if you can find out which cluster you can connect to different activities. So for example, if you find a certain cluster with a jump in the elevation, that will probably be connected to a bulldozer. When something is stable, it can most times send a possession, or if it is going down, it will probably be erosion. We have been doing a lot of research in the stability of the laser scanner. So we try to get it is quite easy to do a lot of corrections in the point cloud, but I think it is more easy to try to correct it before you put it in the point cloud. So, for example, this is an example when there's stormy weather and the instrument is going to shake. So what you like that when the scanner is going from left to right is doing like this. And Mika has been trying to find out what the arrows are. And what you see that although the vibrations, the instrument is bolted to the wall, you still get very small vibrations. But they're very hard to get out because it is a wave pattern when the lesson is going from left to right. So I'm very anxious if somebody finds a very good routine to filter out stuff like that. But yeah. One of the things we have been trying to find out, we are looking what is happening on the beach, and one of the stuff we find very interesting is the effect of people. And one of the things we have been looking at is bulldozers. Bulldozers make very small changes on the beach, but you never know why. So you have a huge point cloud of, I don't know, 30,000 scans, and then find out on what time bulldozer is working. So we have done that in combination with the camera. So we have some pictures on the left. We have called a routine called YOLO to detect bulldozers, and then at the same time try to find the same disturbance in the point cloud. And on the right you see an example of changes on the beach, and so everything in yellow are changes more than 30 centimeters. And if you compare these with the clusters where we detected the bulldozer, the clustering is quite good, but the problem is that we only have, for example, a certain number of times with the bulldozer and other times with the laser scanner. So there's always a discrepancy between the information between the two. But we have been working with Katrien Anders. He's from the University of Heidelberg. He has used this data a lot to define a new method. It's called 4D object supply change. And what she does is she makes timelines from consecutive scans, and she's looking at jumps in the height. And by using by dynamic time warping technique, we're trying to cluster these together. And so, for example, on the left you see same beach again, and the dark brown, that is an intertidal bar. So that is a bar which is comes into the intertidal area. So she finds one point, and then by the clustering, she's able to cluster all these data together. And these techniques we have been using, one, for example, is trying to, if you have 30,000 point clouds, you find all kinds of these objects. They have certain properties, and by self-organizing maps, you can try to find when something. So if you have a certain activity, so something is going up or going down, then it is a clustering of your data that you can reduce the amount of information in your point cloud to activities you like. That has also recently been published. This is a little bit more my field. I'm coastal engineer, so I'm really looking what is happening on the beach and trying to understand it. So this is just a small picture of what is happening at the same time at the beach, which is a lot. So I'm not going to in detail, but the problem is that because there's so much happening at the same time, it is quite hard to follow, and that's the idea for the laser scanner. So you put it there, and then you have lots of data, and then I try to filter out certain specific stuff of this. So I'm now looking at the intertidal zone. So that is where the tide is going up and down. And one of the things we found for the first time, this is also, I think, a world premiere, is found we could follow an intertidal bar. An intertidal bar is just a bar which will just walk in from the beach up to from the sea to the beach. But what is also nice is that you can also follow through time. So M1 is one coming in, M2 is growing, then M3 it is becoming wider, and then with M4 and M5 it is disappearing again. And I think this is the first time it was measured in such detail that you could also follow it, but because we don't measure that continuous on the beach. So what I'm now going to show you are 8,000 scans consecutive, and you're looking at the difference compared to the first scan. So if I have the second scan compared to the first, there's no difference, it is white. Everything is red, is increasing, so that means that it's sand from sand and the other way around. There are a lot of physical processes, so I'm not going to in detail, it's just more to give you an overview of what is might be happening. On the bottom, you see the slope of the beach. So you can, the red one is the first day, and then the blue one is what you get a little bit of an idea what the beach is doing. So what you see on the right is filling up of the, we call it ditch, so there's a little hole. So wind is blowing from the left to the right, and is blowing sands to the right, and that will fill up the right. You see that the blue line is above. And what you also see above is that it's becoming red, which means that the beach is growing. But after a while, you will see that there's also a lot of bulldozing done. See how far past it is. What you also see is that the laser scanner, although we did a lot of correction, that it is still shaking a lot. That has to do, we use fixed objects in the point clouds. And if the fixed object is not there, or we can't find it because it is not visible, then most of my routines have a problem finding the correction. And that's why you get shaking in the data. So yeah, so here you see all the sand moved back again. So there's a lot of stuff happening. So the physical processes, so people, the recreating, the bulldozing, and trying to find these all in the same time. So what we have done, for example, is use these 4D objects, trying to classify. We have been using that technique to look at when sand is increasing, so when there's more sand. And what we have done here is, for example, make the 3D plot where you see the X is from the sea to the beach, and then the Y is along the beach, and then in the height you see the time. For example, what you see is that every sphere gives the size of how much sand is accumulating. But it also means, for example, all the yellow is bulldozing, so it moves again. That is still seen as something which is increasing in sand, but it is not done by the wind, but it is done manually. So this gives a little bit of an idea what is happening on the beach, and then you can make a little bit of separation between what's done by nature and done by hand. We have done some visualization. So what you see on the left are these little wiggles. We call them sand strips. They are phenomena which occurs when the wind is blowing. So you get these little sand waves. And we have been trying to visualize them in this is done in ArcGIS. But that is mainly based on color. So we don't do any reduction on information or something, but we try to see how can we use color, and there are many other techniques. But this one focused on color. And we also, but that is more the detection, when we see them, we also try to get information out of it. And that goes more into Fourier. I'm not sure people know Fourier analysis in 2D, just to get an idea how large it is, how high it is, and in what direction. And that gives us information, for example, how much sand is transported over the beach. And then finally, this is an example of a bigger scale. So the sand strips are, I don't know, 1 or 2 hours, 12 meters wide, 20 centimeters high. This is on long-term effect, 2 years, the effect of buildings, which are quite large. So that can be from the small box in the beginning to the container to the beach hut pavilion. This is 2 years. And what you see here, for example, you see in A, you see a dotted line, which is part of the dune. And if you look at C, you see that on the left side, there is a growth. So between the dune height in 2019 and 2021, there's a growth of the dune, and on the south side there is no growth. And we're trying to investigate what the effect of large-scale buildings is on the dune development. So this has been a little bit of an overview of what we have been doing with our point clouds, which is a little bit more in the physical interpretation, but I hope you like it.
Thanks really for the overview, and are there any questions? Edward?
I'm trying to see if there are any people here.
Hey, Sander.
Hi.
Thank you for your presentation.
Yes.
Also for keeping or stating far more information about the data we use. I have two questions. First of all, your laser scanner sometimes it moves a little bit.
Yeah.
We will store whatever. And they use fixed points somewhere. How do you do that? What are fixed points?
The fixed points are, for example, there can be a concrete floor or a building, or you like something in your point cloud that doesn't move. There you know it doesn't move. And for example, dune is always moving, so that's why this kind of stuff is quite hard to do in the dune area. So we try to find areas which are stable during the whole period, physical objects, and then you try to identify them in your point cloud. And if you know that part of point cloud didn't change, then you can correct it back. But the problem is that you don't know if the shape in the point cloud is always the building.
Yeah.
And that makes it quite hard to.
And the last question is very nice to see the work of Inka Schrijver. If you now compare the different analysis you have performed in the data,
Yeah.
Which part have been done directly on the point data, and which part have been done on maybe a derivative like raster.
I think that Mika has been more working on really on the point cloud data itself, just trying to find information. I didn't show everything here. There's way too much, and I've been, I think, more working on the derivatives. So producing the point cloud and the derivative. Mika has been more working on the clustering and trying to. She's now working on timelines. We call that a loss of log. Which is a technique. So, for example, you look at one point in a timeline and there is a jump, you call it a loss of log, which comes from radar, and then you can, based on the log of log, on the steps and how long it takes, you can try to investigate what is happening. So, Mika is really more working in the point cloud with Roderick. No. No problem.
Thank you so much. I had a question. Sometimes really great research like this gets stuck on really minute details. So if you, and you may or may not have encountered some of these things. I was wondering if you encountered some interesting blog with using point cloud data that might be really insightful for a room of point cloud developers.
Yeah, that can be twofold, because I'm a producer of point clouds. So I just produce something and then you get the point cloud. But if you start with point cloud, there's a different perspective. So one of the points I found quite frustrating is getting, for example, the movie I showed with all the wobbling, trying to fix that. But the problem is then you fix it and then you have another 200 scans and there's another wobble, and then it is you need to spend more and more time to correct the last errors. So that is the most frustrating, maybe from my point of view, to get a good point cloud.
Is that fixing kind of registration over time, spatial temporal registration?
Yeah, the problem is also that you're measuring real activity outside and you're using instruments. So the instrument is not 100%. So you're missing information which you need to make your point cloud. And then it can be the weather, or it can be other stuff. For example, when it is raining, I have a lot of problems with my dereferencing, because I don't see any objects anymore, or I see little. And if I only have 3 points Is that something, is it noise, is it a person, is it what I'm looking for?
And the problem is that harmonization between all the layers.
Yeah. And can of course just don't correct it, but I try to get the highest accuracy because then I can measure it.
In the Kijkduin data, you were saying it was a certain time interval, but I was thinking people were monitoring the percentage and really forever.
Yes, but that's on the cameras,
Optical cameras.
optical cameras, and in a way you get 2D information, but this isn't so far new that we have 3D information.
Yeah.
And
But the latest scanner now is moved. It's not a Kijkduin anymore.
no, this just at university because the project is almost finished. We are processing 3 years of data, so processing 1 year of data takes me about 10,000 hours. Cluster. So 30,000 scans takes a lot of data.
Okay, we are running a bit over time, so I think it is wise now to have a break. More or less planned break at the 2:45. The only problem is that we have one presentation planned before the break, which has been delivered by Vital, which is following up directly on the data that Sander was presenting. So we'll continue after the break with Vital's presentation. So for the people online, please be patient and we shift then after the break. First Vitali in the program and then the others.
Hoi. Hoi. Ja, ik had al zo vermoeden. We kennen elkaar niet, maar...
Nee, nou ja, ik had het gezicht wel eens een keer gezien. Dacht ik, of we elkaar gesproken hebben, een keer dat weet ik nog.
Ja, voor ons. Ga ik vanuit, ja. So people, it's it. I will shout. You don't have to shout.
So the cookies and the tea and coffee is at the other side. Donuts, even donuts.
Ik wil het iets korter maken. Misschien helpt dat. Ja, het is altijd zo.
Word je het beter? Bij technisch dingetje.
Is het handig als ik mijn presentatie naar jou stuur?
Ik denk het handigste, want ja, met op. Wel net.
Hoe hebben zij dat?
Ja, deze nog. Ja, we hebben een folder hier gemaakt, een map. Daar zitten ze in. Ik hoop dat je wat te zien.
Ja, dan stuur ik hem wel even naar je toe, want anders dan moet ik ook op Zoom en zo. Hè?
We hebben het hier, ja, je kan, dat is ook een optie via Zoom, maar het is handiger en iets veiliger om het vanuit
Ja,
dezelfde...
ik stuur hem dan gewoon naar je mail.
Ja,
Ik ga trouwens de helft overslaan waarschijnlijk. Dus
oké, ja.
Hi, Peter. I think I might leave now, if that's okay.
Yeah, I can understand, Rod, given the time.
If there are any questions, though, I'd hold on a bit for that. But if they've all gone to morning tea, well,
I
afternoon
think
tea.
it is fine to go for the night rest, which you have well deserved now. A good list of research topics at the end. That is rather challenging, but
Yes,
yeah, that's
yeah.
our work. Yeah. Good night and say goodbye to Maria.
I will. Thank you. Good night.
Bye bye. Bye bye, Rod.
Hi, Peter.
Hi,
Hi,
Chair.
Peter. How are you?
Oh, yeah, good.
Uh,
Good. So it's Chinese New Year, huh?
yeah, it's
Bless.
we normally have 1 week off during this festival, and after this we will back to work.
That's good.
So
So
yeah,
some
so you
rest.
have chosen an appropriate time for the presentation, so I have time for this.
Yeah, you don't have to work. That is
Exactly.
so. Yeah, we are still continuing. I'm not sure.
Yeah, nice to see the progress.
Yeah, it's not always going that fast as we would like, of course, but yeah, step by step. And there is some. I'm not sure why this. I have to enter a code here. Maybe I'm too slow with typing. Not sure what is happening. But you are having a good time at Alibaba?
Yeah, well, yeah, actually we share a lot of things in common actually. So I'm now also responsible for discrete grid global grid system. So we have also researched about that actually, made some development.
Yeah.
So DGGS.
Yeah, we did have some earlier work on that.
Yeah. So that's somehow mainly that's starting work for me because I have to learn programming.
Do you remember that there was some thesis on this discrete global grids some time ago?
Yeah, by your master student.
Yeah, one of the master students.
Yeah, is that a grid system proposed by you or already used by Fugro?
No,
so it's only for
kind of new approach because it's a kind of 3D or 4D discrete global grid. So it's on the surface and the tessellation of everything. But it is adapted to be able to also have elevation and temporal aspects. So in that sense, it's a bit richer than the standard global grid. And therefore, it was also published in a journal. And I think I now have to be careful. I think the presentation is the last one here, so it should be number 9, if I'm correct. So let me check. Yeah, that's the last one. But it must be late at your side, right?
Yeah, it's already 10 o'clock at night. I think I will. Yeah.
See how long you can endure. We have still some nice stuff to come.
Yeah.
Yeah, Vitaly has been focusing on change detection and how to do that. So quite nice. Yeah, we are already a bit behind schedule. Hi, Marcus, good to see you online. Marcus Schutz.
Yeah, hey.
Hi.
Sorry for joining late.
No problem. I just want to warn you that we have moved the last presentation before the break to after the break because of time issues. So the other people are now in the coffee corner, drinking coffee and eating the cookies, and I will join them in a moment. So we start at 3:15, so in 13 minutes. Then we first have Vitaly. And then the next one is Edward, and then you. You will be then the third after the break.
Okay, I see.
Yeah, and so it should work. And the other people are now in the room. So you are the only remote presenter this afternoon. In the morning, there was Rod Thompson from Australia, and I had some issues with the sound. So somehow the cable to the speakers in the room do not work. I'm not sure where is the problem, but I put the microphone close to my laptop, and then it was reasonably well possible to hear. And with the questions afterwards, I give the microphone to people in the room, and so you should be able to hear them well. Okay, I get a coffee and see you in 10 minutes or so.
Okay, see you later.
Bye. Yeah.
Okay, welcome back everybody, both in the room and online. As promised, it is we have a bit delay. But now we get the presentation of Vitali, who will be showing what he did with the post and data, the data set that was already introduced by Sander. Vitali, the floor is yours.
Thank you very much, Peter. Well, thank you very much. I will.
Is the microphone on? I'm down to. Yeah, say something.
Hi, hello.
Yeah, please. Yeah.
Okay. So, thank you very much. I will talk about some analysis, some preliminary results in the database that already was introduced. So firstly, well, the spatial-temporal analysis allows to detect changes in hotspots, spatial extents, change rates. The detail of this analysis relies on the temporal and the spatial resolution, which is crucial in certain phenomena. Point cloud data allows detailed analysis due to the massive amount of information that can be collected, but most of the existing spatial-temporal analysis methods and examples have been developed or applied to raster or vector data. So to the use of point cloud data has not been fully explored. So there are still some questions to be answered. So as initial steps in this project, 4 use cases have been proposed. Together with Deltares, we decided to these two, firstly, global reservoir monitor analysis, the coastal monitor, and then to automatic identification system data analysis and indoor navigations. I will talking about the second case study. So firstly, I am starting exploring the file-based applications to gain some experience and move to more database solution as the Martin and Thijs have been explained. So the case study, I will not consume too many time because it was already introduced. This is the kite-down beach system. So there are the scanner on the top of one hotel, and the time resolution is 1 hour. So as a data preparation, so we have here some statistics. Basically, we have the data runs basically from 2016 until 2017, from November 2016 to May 2017. So we have one last file per hour, and this data is stored in folders, 1 folder per day. As you can see here, yeah. So as you can see here, since the beginning of 2017, we have more points here, which corresponds to a second scan that is collected at noon, basically. So we have, for this hour, we have 2 scans. One with the same resolution, and the second one with more or less 10 times more points. And this extra file is also stored in every folder. So before to conducting the change detection, we have to be sure that our surface is at least free, or at least with enough information. This is just a conceptual model because we remove some noise from the data set. So basically, as you can see here, we have a big clusters, but the way we propose a clustering technique to group the points and to detect those that refers to noise. So we have a cluster, the biggest one, which corresponds to the beach and the surroundings, also includes the people, pets, the beach items, and whatever, because this algorithm and this method is not aiming to detect or to separate the different beach items or objects. Second cluster, which corresponds to noise, that is close to the where is located the scanner. And also there are other objects, could be cars or whatever, and of course related points and some objects in the ship. So this is the orientation. We have the X, the Y, and the Z. So this is basically our Y, and the X, which is the profile of the beach. So for this methodology, I use the distance between points as the inclusion or exclusion parameters, and I test different distances. And for each cluster, the following was calculated: the number of points, the points percentage, different range in X, Y, and Z, the centroid of the cluster, and the time cost of the clustering. So this is just some results. So basically, in order to identify the optimal distance, we need to analyze these results. No, this is our conceptual model. The biggest clusters here, the results are the cluster size of the 6 biggest clusters and the points percentage. So according to our conceptual models, of the beach, the biggest clusters corresponds to the beach and the surroundings, and the second one to this source of noise. So for large distances, so we see this the identification of these two clusters, but the range is very wide. So in distance equal to 20, the range tends to be not really wide, so it's more consistent. So that means that the median tends to be the same. And of course, for small distances, we start to detect or to break these biggest clusters, and then starting to identify another groups, people, bulldozer, and so on. But this is not the objective of this methodology. So in this case, we are aiming to detect or to identify the optimal distance that allow us to identify the biggest sources of noise. So in these results, we are seeing the centroid. In this case, just two components, the X and Z. Why? Because according to this conceptual model, the centroid of this cluster is more or less around, let me see my notes, but it's something, well, in the case of X, is more or less minus 100. And in this case, the centroid of noise is close to 0, because the coordinate 0, 0, 0 is here in the top of the building, and this source of noise is very close to the source. And in the case of centroid, the centroid of the beach is something like minus 30, and again, the centroid in Z, this noise is 0. So basically, D equal to 20 is an optimal distance to detect this source of noise. So this is just one example of how it looks. This is the points colored by the level of the cluster. So we have a biggest one, which is the beach and the surroundings, and this is just one source of noise. And also, this is some other results, because we are seeing here the number of clusters, the number of points, and the time cost of the clusterings. of this procedure. And basically, what these results also allow us to classify the files. Every point is one last file. Allow us to classify the last files by the noise quantity. So we have the blue one is the files with little noise, the orange with moderate noise, and the red one with much noise. So basically, this results shows that the clustering technique is good because there are some files with considerable quantity or a number of points, which leads to increase the time in clustering. So this is just one example. This is one example with little noise. It's around 1 million points. And this is another example. It's also 1 hour. As you can see here, there are 3 million points. Basically, all of them are noise. So that's the reason that we use this result also to detect those files when we have noise in order to avoid the calculation. And regarding the chain detection, we have different algorithms to calculate the distances between 2 point clouds. And these algorithms go basically from very simple approaches with, for instance, use the nearest neighbor distance, and then go to more complicated algorithms where the neighborhood is modeled with different type of surfaces. So basically, in the simple approach, here we have these blue points is the reference cloud, which can be the point cloud at the time t, for instance, and the red one is the compare cloud, which is the point cloud at 10 plus 1 time, for instance. So basically, in this approach, for every point, p point, the nearest neighbor is found, and then the distance is calculated. Regarding the local modeling, well, basically, for every point, firstly, in the case of the least square plane, firstly, the nearest points are found, which is referred as the neighborhood. And then for this neighborhood, the least square plane is fit. And then the distance between P and the plane is calculated. In the case of the 2.5 triangulation, firstly, the neighborhood is projected into the plane X and Y, and then the 2.5D triangulation is built, and then the distance between P and this 2.5D triangulation is calculated. The same similar procedure for the quadratic, but in this case, the surface follows this equation, which is the reason that also is referred as the height function. And the distance is calculated between this P and the surface. There are another two algorithms that we also consider, the natural neighbor interpolation and the inverse distance weight. Basically, for the natural neighbor interpolation, the Voronoi diagram is firstly computed by using only the reference cloud, and then a second Voronoi diagram is built considering also the P point from the compare cloud, and then the overlapping of this surface the surfaces are used for the calculation of the weights of the set component that is used as the vertical distance. So it's important to note that this method only calculate the distance in the set axis, which is not the case in the other methods, which is the distance is the components of the distance we have in X, Y, and Z. So the same for inverse distance weight. So in this case, the weights are compute with the distance between the point and the reference cloud. And then also we incorporate this multi-scale model to model cloud comparison, where the reference cloud is is not only modeled, but also the compare cloud. So basically the algorithm is similar to the least square, but in this case, all the distances between the reference cloud is used to fit the least square plane. And then all the distances between all these points and the plane are calculated, and then the mean is calculated, which is LS1. And then all the distances between the neighborhood, a second neighborhood from the compare cloud are calculated, and then the mean is computed, which is LS2. So basically the M3C2 distance is computed as the difference between this distance and this distance. So this is, we have and then 8 options. When I noticed, I clarified that the 6 and 7 algorithm only compute the distance in the vertical distance. So the methodology for the implementation, well, basically we retrieve the reference and the compare cloud, and then we model the reference cloud if it's the case. Then we find the nearest points to the local surface, and then we calculate the distance, and we update the distance as the attribute in the compare cloud sample. And for every step, the time cost is calculated. So this is just some preliminary results. So we have the reference cloud, the compare cloud, and this is just one comparison. The magenta points are from the reference cloud, and the green one from the compare cloud. So this is just one example. In the plane Y and Z, Y is this axis. So basically, all those distances above 0, we are calling the position. Below 0, erosion. As you can see here, the range from the M3C2, which is the most elaborated algorithm, the range is smaller than the rest. And you can see here that's the natural neighbor interpolation and the inverse distance weight are those that the distances are bigger with respect to the rest. How it looks in the 3D perspective, well, it's based, we can see here the M3C2. This is just the distances. So we have here the range is smaller in this case, and for the case of natural neighbor interpolation and inverse distance, it's a little bit or much bigger. You can see what happens if we compare point to point from all the algorithms. Well, basically we can see here that at least the M3C2, we don't have similar results with another algorithm. But at least we can identify here that linear interpolation and the 2.5 triangulation, they look very similar. So we can avoid the use of one of them. If we compare the natural neighbor interpolation and the inverse distance, in this case, they are producing very different, which are these two, very different results. And how they look if we use the compare set, but coloring by the position and erosion. But at least here, I cannot see still something because we are plotting all the changes. So we need to use a color scale, a better color scale, in order to see or at least to focus on those maybe the biggest changes, to discriminate those small changes, because at least we can see here that the whole beach is very dynamic. So there are many changes. So we cannot focus in all of them. We need to focus on maybe to start to use some classes. So conclusion and future steps. Basically, we start to use the scan data. We perform this data filtering or clearing approach based on clustering, and we explore to test the cloud distance methods. Next, future steps. Basically, we have to complete the analysis for the entire database, sorry, including the high resolution database, which is the second scan to perform maybe daily in a daily resolution, and also to explore the database approach, because in all the queries and calculation, I'm following the file approach. So I'm retrieving files and then I perform the calculations. So I need to explore the database approach for performing the queries. And finally, to test the algorithms for the calculation of distance with the AHA database. Well, thank you very much.
Thanks, Vitaly, for the presentation, going in detail in all the change algorithms. Any questions? Roderick?
Thank you, and thank you for your nice presentation. Before you, let's say, show the results of all the distance methods, you also announced that you looked at the time it took to compute that, but I didn't see that back in the results. So I was wondering if you could comment on how much time the different methods took.
Yeah, thank you very much. Basically, I found that more time is consumed in this method. As soon as you start to have more steps in the calculation of the in the algorithm, you start to consume more time, basically. And in this case, you have to consume more time because you have more calculations, basically.
Okay.
And I was one of the things is that I was looking for some algorithm that at least have the similar result that this one, in order to say, hey, this is faster. If you have, maybe you can use it for quick results or quick exploration. But at least for these results, I don't have something still. I don't.
How much faster is to-be triangulation compared to multi-scale model?
I'm not. I still don't know because need to see the analysis. But this is of course a good question. Yeah.
Thank you very much for the presentation. I was wondering, are you going to do any clustering after, because now you have a lot of changes? Are you going to cluster, change together, or are you going to different approach?
No, but that's something that I realized here when you are presenting the previous well, the analysis. I just started to say, oh, I think I can perform a clustering on these results. Yeah, but thank you. Yeah.
Other questions? So if you compare hour to hour, the changes are maybe not so much. If it's a normal day, maybe you also have different time resolutions, the day to day or week to week. See if it's more meaningful. But if it's like this purple, it may be noise. Random a bit. A question. Okay, that's really marked. Now another question. Yeah, what is better, vertical distance or the true distance? What do you think and why? I don't know.
Well, at least I see that depends of the phenomena. For instance, this method is very popular in the landslides. So because it's very important, the horizontal component, not just the vertical. But in this case, at least, I'm not sure. This is something that I have to analyze very well, because if you see here, you have the results are really bigger than the rest. I'm not sure if it's because in this case the set component is low, but maybe because the sun is moving. I'm not sure, because I'm not presenting here the X and Y component, just the vertical.
Yeah. We had a comment we kind of ignored nD-PointClouds because we feel that most of the beach is flat anyway, or close to flat. So as long as you're on the beach, using M3C2 would not add so much with on islands or somewhere in the mountains, and you have like Adrian, you have a slope of 20 or 30%. Yeah, then that would make more sense maybe. So we decided kind of to, but on the other hand, also here we have like higher on the beach. Yeah, then your it gets maybe a bit different. Yeah, let's say
I was also thinking maybe if you want to compute volume change, then yeah, we got that vertical Z difference is more useful, assuming that the point is an average area to which it belongs, which is further away, of course. I didn't know all of that. Just a sense, yeah. Okay, a lot of questions. Let me check if there are online questions. Please, people online, if you have a question, open your microphone. If not, then Vitaly, thanks again. Then let's switch to the next presentation by Edward, which is giving an overview of what happens with point clouds in the education, various projects. So Edward, I will try to find some slides for you. So, floor is yours. Thank you.
Okay, so the idea is that I will show you some of the work done by our students. Of course, we really think that point clouds are quite important. I think everyone over here is quite convinced about that topic. But sometimes you still have to convince others, and it's also our job to convince students about what is important, what's not that maybe not that important. And I focus a little bit about our education. And we as a group, we are involved in the Master of Science in Geomatics and also in the Master of Science in SIMA, New Information and for Management and Applications. And I will show you just some short ideas. I will try to keep it in time. Of course, we are a little bit behind schedule. What you see over here is just one very nice point cloud. We derived it ourselves, or in fact, my son did do so. Of course, nowadays we do have some very nice equipment. We bought ourselves some very nice stuff. I will show you. First, this one over here. Very nice case. And if you open it, it will there's some GeoSlam Set Horizon instrument, a very nice piece of hardware, and also the software with some comes along with it, and everyone can use that. Quite expensive, so don't throw it away, but it works quite well, and everyone can use that. And also we do have an iPad. I will show you some uses about that. So first this one. At the top left, you will see this part of the building. That part of the building at the main entrance. And just one clip out of the point cloud. Derived in, I think, only 10 minutes time. Walk around, and the algorithm, the same algorithm, will do it at your best to combine what you have measured by the LiDAR to one beautiful 3D point cloud. It is also a SLAM, so for me, not only the point cloud is important, but also that you can detect where you have been in the red upper. In the other picture, you will see in red the path you took. So also for indoor navigation purposes, it's a very nice piece of hardware. Nowadays, we also do have an iPad 12 hardware device. I will not open it, but the secret is also over there. Now there's a LiDAR scanner over there. Has been used in education already. Nick is over there somewhere. He created these figures. As part of his module 6 in schema. You will see at the upper right point cloud of the ASN3. There's a building roof type. Then the building was demolished. Of course, it would be a new building over there. So in ASN4 you will see nothing at all. So in the meantime, if you would like to have the building yourself, then you go over there and you take your iPad over there and then you can scan the environment and you will have a kind of a new representation out of that. And again, maybe for education purposes, it is also very nice to have a proper set of apps. I think not only the hardware, but also that the software which is delivered, for example, with the GeoSat separation, but also with the iPad. Yeah, that's very nice. That at least your students will get the idea of that you can have a hardware device and that you can process that, and that you will have a proper 3D data set out of that without doing a lot yourself. And maybe that's good, maybe not. Talking a little bit about students nowadays, you know that nD-GPT is now around. So what is left for education? I did a test last week. So I asked nD-GPT, okay, why are point clouds important in geomatics education? And then it just returns this beautiful overview. I was completely impressed, not only by that it is completely correct, but also that it has been expressed in a very nice English way. So it's really important to have the 3D spatial characteristics of real-world environments, buildings, and other structures used for decision-making processes, and really very useful for education and training in geomatics-related fields. You can go one step further, and we have seen that in the step about, okay, why are point clouds better than just DTMs? And kind of a derivative of point clouds. Because they offer a higher level of detail and accuracy. Point clouds contain more detailed and accurate information about the shape and surface of the terrain, also true. And point clouds are able to capture a wider range of features as buildings, bridges, and vegetations, which are not that present in DTM. Also true. Then, not only about 2D or 3D height, but also 4D. Of course, we would like to add an extra dimension, time. Why? We've shown that, we've seen that already. Hey, we would like to use to track changes over there. And we can do that by having time series animations and perform time series analysis. So, maybe we just should stop our education and just to ask the students to chat with nD-GPT and have this kind of information, and then they don't have to read a reader anymore, or even not a study it. Last question, about not about 2D or 3D or 4D, about nD, our own research, and even that one was very well answered. Of course, we don't only capture the coordinates, but also the cover, the reflectivity, intensity, temperature, what other dimensions could be important in the data set. In our own research, don't know whether or not Peter was at the other side of nD-GPT, but I think also these answers are quite well stated. It's about data capture, data processing, data fusion, visualization, all kinds of applications, scalability, quality assessment, and machine learning and deep learning. About all deep learning. Okay, then still we are doing our own education. In GIMA, Geoinformation Management and Applications, I think Peter shows off the advantage of having point clouds in the very first part, in the module 0. In the introduction, then we do have some topics in module 6 about advanced applications, and of course also in the thesis. I will show you very fast some visuals after this slide.
In geomatics, we do have a little bit more effort in data acquisition and data processing and data analysis and data visualization. So one full course in sensing technologies, one full course in 3D modeling, the built environment, one full course in geodatabase management systems, and also the so-called synthesis project. The synthesis project is a little bit the same alike as module 6 in GIMA. Also one group of students working together for 7 or 8 weeks and having a real case scenario which they should work on that together. And of course also the thesis, which is a little bit more easy than in the GIMA. Then only for reference, and I will just click over that each slide for only a couple of seconds. But I will make it, these slides will become available for you anyhow. So starting with the GIMA module 6, the case studies. Long time ago, we started with these 3 couple of years ago. And the nice thing is that you still recognize, or I still recognize the names of these students. Of course, it seems to be that if they have done their thesis or their case study or the module 6, and then they did do the same like also for the thesis, and also in practice they will still do that. I really like this idea of having a point cloud and to ask where to place the CCTV coverage cameras, especially police system asking for that. To use a point cloud representation for stream delineation. And so again, not to first derive the 2D raster, but then do it directly on the point cloud. This was already been shown a little bit, also with Inge Scheider, who did do her work also with the code scan data, and to make a proper visualization of the changes of the coast can be done. Sometimes students put their own previous work in a bachelor, and I wasn't aware of the gentrification anyhow. But it could be even that if you do have some point clouds for several years, as in 1, 2, 3, 4, 5, 6, 7, 8, in the coming years, that you can even see the changes in the city. And also maybe if you have a terrestrial point cloud or a mobile point cloud data. Used for energy efficiency or event-based change detections, like already been shown. A lot of theses over there to detect unmarked graves. Was a very nice one by Christian Riesner. Mark Burrell, he really did very nice work about maintaining up-to-date distance twin by the use of point cloud data and Inge Vogelsang. Also about dense subsidies. Stijn Tillenhoven, Inge Scheier, I can see there she is, again doing her thesis, and Dirk van Broekhoven. Then also some work by our students in the master program in geomatics, using their point cloud not for visualization but for blind people. Because if you have the data, and you can have the data either with this very expensive one or maybe a very not as very expensive equipment, and you can make that impression feasible and touchable and tenable for blind people, then they can also have a kind of impression of what is around them. Improving inferring roof semantics for more accurate solar potential assessment was a very nice one. And some other topics, but I will just skip those given the time. But the main topic is over there that even if nowadays students can use a tool like ChatGPT to get acquaintance with what is it about, doing it yourself in a kind of a project really is far more important. And working with a lot of data is a very nice learning objective. So that's it from my presentation.
Thanks, Edward. Welcome. Yeah, fantastic to see what ChatGPT
and tell us about difficult questions. Any questions from the audience?
Well, maybe one question on the education at IMA and geomatics, and that's what part of, so they are exposed to point clouds in different courses. But for example, the thesis is not obligatory, I guess, to do it on point cloud. I was wondering what part is all students see, and what part are students seeing that like point clouds?
In geomatics, for sure, all students will have a proper insight in the data acquisition and data analysis and presentation of point clouds. In schema, really only some students are being exposed to it.
Yeah, but they can go in all different
They
directions.
can go in all different directions, yes. Yeah, but some do like it, and some others don't. But they have a free choice, because they can really pick a topic themselves. Yeah, of course.
More questions? And if not, let's move quickly online because we have always had a problem with time. Thanks, everyone.
I did do my best.
No, you did it very well. Nice appendix. And the next presentation is by Marcus Schutz online. Marcus is, of course, very well known from the Poetry Viewer and other point cloud visualization tools. So Marcus, if all goes well, you should be able to share screen, and then we should be able to see it here.
Okay, I'll try to share now.
Yeah, there is coming.
Okay, can you see the right slides, the right display?
Yeah.
Okay, great.
Still a bit in the edit mode.
Okay, then it's the wrong display. I'll try to change monitors. Okay, is it the right one now?
No, it's still the edit version.
Huh, interesting.
It's always magic. And I'm happy to see I'm not the only person.
Okay, but now.
Well, it's still the same.
Okay, that's interesting because I'm going to see both in display mode. I'll try again. Just a sec. Okay, this should be it.
Yeah.
Okay, nice.
Okay, Marcus, the floor is yours.
Okay, so yeah, I'm just showing a little bit about our recent work on CUDA accelerated LOD generation. And the reason why we're doing this here is because the peak LOD generation performance that we were able to achieve on a CPU with our core algorithms was about 11 million points per second. So if you had larger point clouds, that could take quite a while to actually get a LOD structure. So the question here is, how much faster can we actually be in CUDA? And for now, we are limiting this to just measuring the pure GPU processing performance, completely ignoring disk I/O for now and doing everything in core. So just as a first iteration of this. So the data structure that we're generating is pretty much the same as in Poetry. There are some slight differences, but the general idea is the same. We have these octree nodes, and each octree node is essentially a subsample that was created on a grid of 128 to the power of 3 grid cells. So the CUDA approach that we've been trying, and which we'll hopefully publish in the next few weeks on arXiv, is actually largely the same that we did previously on the CPU with the fast out-of-core LOD generation paper. But with the CUDA approach, we were able to do this about 100 times faster. And with all this extra performance, we can now spend some of that extra time on actually generating higher quality results by doing color filtering. So here's an overview of the algorithm. In the first pass, what we're doing is we want to take all the points in an octree and partition that into leaf nodes, which have at most 10,000 points each. And to do that, we simply do a count sort, which is pretty much the fastest way that you can sort points into buckets. It has linear complexity. And to be precise, what we have to do is we have to iterate over all the points twice. Once to count how many points fall into each grid cell, and another time to move the point to the correct location in a sorted list. We also do a hierarchical count sort where we merge cells if they have a very small amount of points after counting. So for example, we want to avoid nodes that have a very tiny amount of points, like tens to hundreds of points. We want to merge them until they're as close to the 10,000 points per node as possible. In the second pass, after we partitioned all the points into leaf nodes, we do a bottom-up voxelization. So previously, we didn't really do a voxelization. We did a subsampling where we promoted points to upper levels of the hierarchy and thereby continuously reduce the resolution. Now we are doing more voxelization, which is not that much different. It's just that the voxelization grid is essentially a quantized point cloud. We're losing full coordinate precision, but for rendering that doesn't matter at all because we're trying to render until we have a resolution of 1 voxel per pixel. And at that point, it doesn't really matter if the voxel is quantized to that resolution. So differences in the CPU and CUDA approaches. So general, the algorithm is largely the same, but on a CPU, the parallelism is very different. So on a CPU, we have about 16 threads that can operate completely independent to each other. In CUDA, we now have, at least on the RTX 3090 GPU that we use, we now have 10,000 CUDA cores, which is considered kind of the threads. So we have 10,000 threads. So we have a lot of threads, but these threads are not as independent as they're on a CPU. So the threads, they're grouped in blocks, and all the threads in a block, they do not operate independently to each other. They do exact the same steps in lockstep. So if you have 128 threads in a block, all 128 threads do first load the point, then they project the point to a pixel, then they do something on that pixel, and they cannot really do something independently. On a GPU, we also have streaming multiprocessors, and each streaming multiprocessor more or less processes one block of threads at a time. And if we want to do work that works independently to each other, then we have to do this on the level of a streaming multiprocessor, because each streaming multiprocessor can do something completely different than another streaming multiprocessor. It's just a thread within a multiprocessor that have to do exactly the same instruction in each step. So my personal mental model of that is, and please do not ever quote me on that because some people will not agree. My mental model here is that a GPU doesn't really have 10,000 threads just because it has 10,000 CUDA cores. And if we want to compare it to CPU, it's more like it has 84 threads if it has 84 streaming multiprocessors, but each of these threads can operate on 100 items at the same time. So if we, for example, if you know about SIMD on a CPU, it's kind of like SIMD, but with much, much larger amount of items. So each streaming multiprocessor operates the same instruction on 128 threads points at once. It's not the entire truth, but it kind of helps reason about how things in CUDA and on a CPU differ. At the bottom here, you can see kind of the different thread blocks that you have, and each thread block then has about 128 threads. And each of these thread blocks can operate independently to each other. So the CUDA port now needs to do a little bit, it works a little bit differently regarding parallelism than the CPU approach. The CPU approach utilized one thread per chunk of 10 million points. So one thread operates on 10 million points. It splits the 10 million points into finer nodes and then does subsampling. And we can do 16 threads at the same time. In CUDA, we do it a little bit different. We have also at least 3 levels of parallelism here. For the counting, from the counting sort, we simply let each thread process 10,000 points. And if we have 100 million points, it means We have 10,000 threads doing processing 10,000 points each until we process 100 million points. For random sampling, we let each thread block process one octree node. So we have, if we have 84 streaming multiprocessors, that more or less means we have 84 blocks that are processed in parallel. So we process 84 different nodes in parallel. For the filtered sampling approach, so not the random sampling, but the approach where we do color filtering, we again use all threads to do one single node. And once the single node is finished, then all the threads work on the next node. This is not optimal. We're still tweaking this one a little bit, but for now it's necessary because this approach needs more memory that doesn't fit into a single thread block. So here's some reasonings on why we choose these levels of parallelism. So for counting, each thread processes 10,000 points. And this is just a trivial case. This is kind of what the GPU is made for. We have millions to tens of millions of items, and each thread takes one item, processes it in parallel, and then takes the next item, processes it in parallel, and 10,000 threads do this at the same time. And all these 10,000 threads do the exact same work. All of these 10,000 threads take another point, project it to the counting grid, and update the counting grid by increasing the counter by 1. So this is kind of trivial and what the GPU is made for. For the random sampling approach, each block processes one octree node. And the reasoning why we do this here is because each streaming multiprocessor, which can operate one block at a time, has its own shared memory. And shared memory is pretty much the same as L1 cache. So it's super fast. And with shared memory, we ourselves can determine what exactly happens in there. And in case of random sampling, what we do is we use the shared memory for the random sampling grid. So we have a grid of 128 to the power of 3 grid cells that we put in shared memory of the streaming multiprocessor, which is the counting grid for one single node, or the sampling grid for one single node. Because the whole grid does not fit into this shared memory, actually, it's just 48 kilobytes, we use a hash map, and with the hash map, this works perfectly fine. So now we have sufficient memory for one node, but not more. So we can only process one node per streaming multiprocessor or per block. And to the bottom here, I took an image from the internet that kind of shows what happens. We have several points that we project to the grid. And for each grid cell here, we take one random points that we promote to the lower level of detail. For filtered sampling, we do this a little differently because the whole grid here, the sampling grid, doesn't fit into shared memory. We cannot use the hash map anymore because the hash map with all this neighborhood calculation and everything and the large amount of memory we need, it does not fit into shared memory anymore. So that at that point, we just thought, okay, forget it. We just use global memory and we let all threads that we have, all 10,000 GPU cores, process it simultaneously. So all 10,000 GPU cores, they take one node of the octree that has to be subsampled. And then they do the subsampling. So each thread picks a point, does the subsampling. If there are still points left, then each thread picks another point. And once this is done, we have the voxels for our low level of detail node. And we finish this node. We clear the sampling grid, and each thread then processes the next node. This is not actually optimal. We're still tweaking that, but it's still a lot faster than doing things on the CPU. So here's the difference of what it looks like without color filtering to the left and what it looks like to the right. So to the left is something you'd usually get to see in Poetry right now. There are several problems here. For example, in kind of in the middle here, there's supposed to be a label with some text on it, but there's the text here is represented as kind of outlier points. So there's some black points that were selected where the text was, but you can't really see the text at all. To the right, we computed average color values. So it looks a bit smeared, but at least we can recognize that there should probably be some text here. So the easy and fast way to compute this is by simply computing the average for each voxel cell or sample grid cell that we have. So we have all the points that we project to the sampling grid, and we compute the average color value. The problem with that is that if we have some outliers here, for example, we have a surface, but only one point intersects with the voxel at the upper right. So we have this one point that has maybe a very different color value, but because the average is of just one point and it's an outlier value, it kind of looks like we have a red point or voxel here, but it's not really true. It's not very representative of the whole surface. So computing the average of a voxel is fast, but it's not perfect for quality. So the slower but nicer way is to compute a weighted average of a 3 times 3 neighborhood. So each point in this neighborhood contributes its color value depending on the distance to the voxel that we're currently processing. The farther from the center, the smaller the contribution. So this is also something that we're still fine-tuning quality-wise, but it's already looking much better in appearance. So let's take a look at this picture here. To the left, this is what we get with Poetry right now. And if you look at the pillar in the middle here, we get kind of random garbage from the color values here. And if you look at the picture to the right here, we can actually see that this pillar consists of rows of stones here. So I hope you can actually see this maybe of your projection. I'll just zoom in here. So we can see that there are rows of stones here that we could not see in this just randomly selected color values. So same resolution, but we still seeing more information here just by computing these averages. Performance-wise, the CUDA approach can do the random sampling for 145 million points in 108 milliseconds, which means that it operates at a speed of about 1.3 billion points per second. So this is about 100 times faster than pretty much the same quality computed on a CPU. With color filtering, by doing the average on a single cell, we get a throughput of about 426 million points, which is about 40 times faster than the version on the CPU, even though it has better quality. And the color filtering approach with the neighborhood can achieve about 150 million points per second. So about 10 to 15 times faster, even though the quality is much better. And yeah, that's it for now. So we're still finalizing the paper, hopefully out in the next few weeks on archive and maybe some improvements and also better figures to better understand what we're actually doing here. So thanks for your attention.
Thanks, Marcus, for the presentation. Are there any questions from the room for Marcus? No.
Hello, Marcus. Thank you for the nice presentation. Just wanted to know that because I'm also working on the Poetry converter, is still the indexing the bottleneck in this CUDA implementation? In other words, the main component that takes time in this in your CUDA implementation. And how is the contribution of the counting? Because the counting in your CPU implementation, you're doing an atomic add. Is it not costly, very costly in the case of CUDA?
What was the last part of the question?
Sorry, I'm talking about in your CPU implementation, you're doing an atomic add when you increment the grid during the counting phase. Isn't it very costly in the case of CUDA, or you found it to be not so?
The counting is actually super efficient on a GPU. It's much better at counting. We have some atomic adds that can do, so we just do 10,000 threads, they do the counting, and they do atomic adds. There's no kind of issues with threading. It's very efficient. So counting is pretty much not a bottleneck at all. It's mostly the sampling that is the bottleneck. The random sampling, not so much. That's super fast. It's as fast as the counting. But once we do the higher quality sampling, we run a bit into bottlenecks. But mostly the bottleneck then becomes clearing the buffers, clearing the sampling grids. Because for each node we have the sampling grid. It's 128 to the power 3, even though just a fraction of it is actually used. And for the next node, we need to clear all of that. And if we do this for thousands of nodes or 10,000s of nodes, then the clearing becomes one of the main bottlenecks. It's not a bottleneck with the random sampling because all of that is done in shared memory. And in shared memory, that's no issue at all. And also because it's with a hash map, so much smaller amount of memory that has to be cleared.
Thanks for the answer. Marcus, I was wondering, you explained that you were going to levels of detail, and were these discrete levels of detail, or are you also thinking about continuous levels of detail because you are tree building, if I understand?
Yeah, there's discrete levels of detail. So the continuous level of detail was no consideration at all here.
Yeah, and when looking at the image, somehow you seem to drape on the surface of the objects in the scene, this kind of texture. It looks like texture, and like, yeah, exactly. It does not look like a point cloud anymore. The point cloud feeling is a bit gone.
Oh yeah, that's true here because we've switched a little bit to voxel rendering here. It's kind of, in a way, it's still a point cloud. It's just quantized coordinates, so it's more like a voxel model now. But the intention is to render this voxel model at a resolution of 1 voxel per pixel, and at that point, it really doesn't matter anymore.
Yeah, yeah. When the voxels get super small, they are kind of like the point again. Yeah, I see your point.
And also, the highest level of detail are the leaf nodes where the original points are. So as soon as you zoom in, you will still get to see the original points, and yeah, so just a normal point cloud.
And in this image, is this a single level of detail, or are we seeing multiple levels, say nearby, finer, further away, less detail?
This right now is a single level of detail.
Yeah. Okay. More questions, either online or in the room? Then, Marcus, thank you very much for your presentation from Vienna. And we continue with the next presentation, which is by Naumann. And I will switch the slides here. You can do the headset or the microphone, what you prefer. Yeah. Switch up the microphone. Yeah.
Thank you, Peter, for inviting me for giving this talk. Actually, I am Naumann Ahmed. I am a research software engineer at the eScience Center. And today I will be discussing some of the work that I've been doing on the supercomputer. It is mainly studying the poetry converter, and I will also be talking about my first initial MPI implementation for the poetry converter. So as we have that supercomputer that at TU, which have different kinds of nodes available. For supercomputing, we have a standard nodes with 48, which are total number of nodes are 48 in total number of nodes are 218 in the standard category, and each node is a 48 core Intel Xeon processor. It has a 192 gigabyte of RAM and a 480 gigabyte SSD that is directly attached to the node. Then we have a high memory nodes as well. For example, we have a FAT type A and B with lesser number of nodes. The number of cores per node is the same, but much larger amount of memory. So nearly 1 terabyte, more than 1.5 terabyte in FAT type B. Then we have specialized nodes that contain GPUs. We have we have 10 of those. Each has a 48 core CPU, and with the CPU we have a GPU attached as an accelerator. we have two kinds of GPUs or two per node, two AMD GPUs per node plus four NVIDIA GPUs, and they are all high-end GPUs. The RAM is a bit low. It is only 32 gigabyte. So some additional more specifications. The interconnect between the nodes is quite fast. It is 100 gigabits per second interconnect node. Each account is given a 5 terabyte of storage, known as the scratch memory, with a throughput of at least 20 gigabyte per second. So if you multiply it by so the throughput for this scratch memory is roughly the same as the interconnect between the nodes. And then you have a 200 terabyte of pure Delft storage. So this is what we have available for computing the point clouds on the Delft View supercomputer. You have been given a 200 terabyte of pure Delft storage, which is connected to a scratch memory via a slow connection. So you can download and upload data from the scratch memory to the Delft storage, or from the Delft storage back into the scratch memory. So in this Delft supercomputer, I have been mainly studying and trying to improve the performance of the port converter 2. As Marcus explained, so it has several stages. So you have an input, you have a counting phase, in which you have a 3D gate. Over here it is on as a 2D gate, and in each gate you try to count the number of cells that belong to a grid cell. So this is the counting phase. Then you merge the sparse cells. So you have some cells which have less number of points, less than a certain setting. So you try to merge them. This is the merging sparse cell phase. And then what you do, you distribute these. This is actually an IO phase, distribute points, where you write these merged cells into separate files. And this is known as the distribute phase. And then you have the main phase, which is the indexing phase, in which you build up the octree, starting from those chunks that have been created in the distribute point phase, each one file per chunk. You try to build an octree, starting from to try to build an octree out of that, which is known as the indexing phase. And then the final merge part as well, because each chunk is computed independently, and it is and the global, and it goes up to a certain node, and it is actually a certain node in the global octree. And then you need to have a final merge phase where you merge all those root nodes that have been computed by the indexing phase. That is the final merge. That is different from the merge parcel. So we are interested in computing the whole AHN3 data with the port, for example, with the port converter on the Delft View. The specs are, we have a 2.3 or roughly 2.4 terabytes of AHN3 data, which is splitted on over 1400 large files. And we have all this data already downloaded in the Delft storage. We get 200 terabytes of storage. But the issue is we can't compute it over there. We have to load that data into the scratch memory for the computation purpose. So what we did is that the current implementation of the port converter 2 is for a single node. It runs on a single node, so we try to measure performance for a single node. So this is a very small subset of the AHN3 data. So it is 1 billion points with a size of 5 gigabytes. So we use 12 threads on a standard Delft View node. So in the standard category of the Delft View nodes, one of out of those 218 nodes with 48 cores per node and a 192 gigabyte of memory. And because actually the dense computer is always occupied, and you will not able to get all the 48 cores for your processing, or in other words, you can not be able to get a full node for the processing purposes. Then for measuring the Portree converter performance, we use the sampling method, Poisson sampling method. We use the compression brought. In other words, the output is compressed. Otherwise, it is too large to fit on the scratch memory. And this process took just 11 minutes. The output format of Portree converter 2 is a proprietary. And based on this calculation, we predicted that for the whole HN3 data with a single node would take about 4 to 5 days, depending upon the load on the supercomputer. So then we measured different kind of we measured the CPU, RAM, and disk utilization of the Portree converter 2. On the x-axis it is time, and on the y-axis it is the CPU utilization in this graph. So it starts with a counting phase and a distribution phase, followed by a merge phase, followed by indexing phase. So you can see that in the initial phase you have an average on average you have a low CPU utilization because of this is happening due to the lot of I/O in these phases. Then after that, when it starts into the when it enters into the indexing phase, the CPU utilization becomes better. The RAM utilization is about, the peak RAM utilization is about 25 gigabyte, and it happens during the indexing phase. Now, this is the important issue. The disk utilization is 10 times larger than the input. For example, 6 times larger than the input data. In other words, that I'm going to explain later, that you can't do the whole HN3 data in one go. So because the peak disk utilization is about 6 times the input data. This is actually kind of a temp data that got deleted as the time passes. The final output of that is broadly compressed is about 2x larger. So if you have a 2.2 terabyte of input data, the final output will be about 4 terabytes. But the issue is not this. The issue is the temporary disk utilization. So we have low CPU utilization during the chunking and during the pulse. Sorry, this is not chunking. This is the counting and distribution phase. Sorry, for the typo, this is the counting. But it doesn't matter much because it only takes 25% of the total runtime, the counting and the distribution phase. So if you have a low CPU utilization, it is not an issue. So you have a low RAM utilization. Low RAM utilization in the sense that we have 192 gigabytes of RAM on per node, but normally it do not take more than 40-50 gigabyte. The Portree converter do not utilize more than 40-50 gigabyte of RAM. So we have extra RAM available on system, then we can utilize for better performance. So how can we do that? For example, we can maybe the Portree converter does a lot of I/O. It writes to the disk and then reads those disk files. So what we can do is maybe that we can, rather than writing to the disk, we can memory map those files. We can write those files in a memory and then read from the memory in the distribution phase. And for example, when we writing as an output of the distribution phase, the chunk files, we don't write them in the memory. In the files, we write them in the memory as memory mapped files, and then the indexing phase reads from the memory. But the whole point is that the 75% of the time is spent in indexing, out of which 70% which is out of which 70% is based on a standard sort algorithm that is being performed during the indexing phase. So in essence, standard sort is a optimized implementation of a sort algorithm by the standard library. So in essence, single node performance has a little room of improvement. So you can apply a couple of tricks on that. Maybe, for example, in the counting phase, you can have all the threads are trying to write to a single grid cell. You can avoid that. You can have a separate gate for each thread, and then you try to accumulate you try to add up all the gates. And secondly, maybe reducing I/O with the same method I told you, rather than writing the files to the disk, you memory map the files. But there's still a small room of improvement, because this will not improve more than 25% of the time. So the way to go is to use MPI. For example, because you have a lot of resources and available in the Dell supercomputer, and you can't even fully occupy a node, because these resources are shared. So you can't get more than 12 or 20 threads per node. So you have to split your jobs across different nodes. You will get at least 12 threads on different nodes, but not all the threads on a single node. So what and it has a disk utilization issue that I previously explained, that the peak disk utilization is about 6 times larger than the input data. So we can't do the 2.4 terabyte of HN3 in one go on a 5 terabyte scratch memory. We can do it in 4 rounds. Maybe in 4 rounds is to split the input data in 4 parts, run the Portree converter till the indexing phase, only till the indexing phase, when it created all the partial octrees. We save those partial octrees into two Dell storage for 1 round, then for the second round, then 4 rounds, and then finally we load finally, after completing all 4 rounds for doing all 4 parts, we load only the hierarchy information from the TU-Dell storage and build a full octree out of that. So what we did in our initial implementation of MPI is to target the indexing phase, because it takes 75% of the time. And the good thing about it is that you have different chunk files. That is an output of the distribution phase, and each chunk file is computed independently by a thread in the original implementation. So it is computed independently by a thread. So you can easily distribute it with the help of MPI over the Dell supercomputer. So this is what we did. We did the indexing phase on multiple nodes. And keep in mind, indexing node will create the partial octrees that have to be merged by the final merging phase. But that final merging phase has negligible time, takes negligible time. So with 75%, we can expect a maximum force speed of 4x, because we are not touching anything with the 25% time. The input and settings are for my results that will be shown on the next slide, is that we now have used 20 HN3 large files with a total points of about greater than 10 billion, with a total size of 50 gigabytes. Again, 12 threads on a standard Dell Blue node. 12 threads we have requested 12 threads per standard Dell Blue node. And again, we have used the sampling method as Poisson and compression, Brotli compression. And this is some preliminary results of the MP implementation. With 2 nodes, we can get about a 1.5x improvement over a single node. With 4, it touches 2. And with 8 nodes, we are able to reach about 2.7 times speed up as compared to a single node. So this is what we plan to do in the future. We would like to have a full implementation, because if we only accelerate the indexing phase and don't touch and leave the distribution and the counting phase as it is, it will become a bottleneck. So you have to do the full Portree converter to on the with the NPI. I will not suggest to go to the path of trying to improve a single node performance of Portree converter 2, because that would may complicate even the if you're trying to improve a single node performance, it may complicate the MPI implementation. The MPI implementation may become harder if you do all the memory mapping kind of things rather than writing to disk. Another thing we will be looking into that again that I just mentioned, that solve that disk space issue. You can't do the whole 2.4 terabytes HN3. You need at least 4 rounds. Then write the output to the disk storage, load the hierarchy information finally, and build a final octree. And I'll be also looking at the Martine's SFC representation of the point cloud data and try to scale it on the desk view. And I initially also worked on the Untwine. Untwine is another converter that converts the input last data into an octree representation. I initially also worked on that, but it has poorer performance as compared to the Portree converter, although the output is a COPC large, which is much smaller, which is nearly as large as the input data. But its performance is not good. Maybe we can, if we find, we can look into further improving the Untwine performance as well, and look into what is causing its poor performance. Yeah, this is all from me. Any question?
Any questions? No one?
Thank you. I had one question. I think you mentioned in your talk that most time actually was spent on sorting. So I was wondering in what order is HN distributed, and in which order should HN be distributed?
Actually, that sorting happens during the sampling phase. You have an indexing, what you happen, you have the parcel octree is built bottom up as shown. So you have a node, node at a higher level of detail, and you need a node at a lower level of detail. So you need to sample it, for example, using a Poisson technique. So for that, and during that phase, it does come some kind of sorting. That takes most of the time in the indexing phase.
And so it doesn't help if at HN they would distribute it in a different way, because you always have to build up this octree.
Yeah. You have to also always do that. Yeah.
Any other question, Martijn?
No, thank you for giving the overview. What do you think that will happen if we also try to incorporate time in the octrees, for example? Would that be possible with these tools, or are they just processing X, Y, and Z, and that's it?
I have thought about it. What I would say is that we have to, we have to build a separate octree for each time step. This is the only way I can see it right now. Because in the next time step, you can't guarantee that you will get the same X and Y values, because scanning is different at every time step. So it would be different with the octree representation. Yeah, it would be different. So you have to go to other models. Maybe the SFC representation would be more suitable for that.
Any other question? Maybe Marcus online, because it's not about the tools, Marcus.
No question right now. It was very interesting, but I'm always having a bit troubles acoustically understanding online presentations. So maybe next time when we meet in live.
Okay, I'll make sure the slides are being shared, and also the contact information. Are you aware of other activities on supercomputers that people try to speed up?
For the point cloud data project, or for
point clouds in general? large data sets to process the large point cloud data sets?
No, not in my knowledge, except this presentation from the Marcus that we have seen today doing, because we can also use that in our TestView supercomputer using the GPU nodes.
Yeah, that was my exact question.
Yeah.
How would these supercomputers utilize the CUDA solution that Marcus?
We have these 10 CUDA nodes available in the TestView supercomputer, and Marcus implementation could be used, and maybe on top of that because we have 10 nodes, we can combine CUDA with MPI as well. So it would further, so we distribute the task on multiple CUDA nodes.
No more questions? Okay, then now, thanks again. I will switch the slides to move on. And now we get an impression of what is happening at the site of Esri, which is one of the major GIS company, and of course also active in PointClouds. The floor is yours.
Yes, thank you very much. How's the energy, guys? I have a short presentation, I promise you. We will have a look at the developments on PointClouds in ArcGIS. Actually, we support them for a very long time already, of course. So I will be focusing on two things. One is working with PointClouds in ArcGIS and what is happening around deep learning and stuff like that. And next on something we are going to work on this year.
Excuse me, can you please share your screen?
Oh, the screen is not shared.
It's my fault. Huh?
One moment, please.
Sorry.
Yes, thanks. ArcGIS Reality, which we will work on this year, and where PointClouds can also be, LiDAR can also be at play. First, what do our customers do, for example, and what have we done in the last few years? It's, for example, possible to take aerial LiDAR to construct buildings, and in this case, the LiDAR is first rasterized, then manually digitized, and from there we make a 3D reconstruction of buildings. Well, this digitizing is very time consuming, and that's why we can use deep learning within ArcGIS to do the digitizing via mask RCNN in this case. So we embedded a lot of machine learning frameworks within ArcGIS. So you can think about PyTorch or Keras or frameworks like this, which makes it possible for us to use, for example, mask RCNN, but there are a lot more. And this makes things a lot faster, of course. But in this example, we first rasterize the LiDAR, but is it also possible to work without rasterization and directly with the 3D LiDAR point cloud? This is also possible in different ways. And here we see the traditional way, I would say, which contains a lot of steps, which I will not dive into right now. But the first two are to classify the ground and the buildings with some tools. And at point 8, we create a multi-patch. These multi-patches are created from those point clouds, and therefore you see a lot of noise in it. So you can imagine this. So it's very difficult to edit these multi-patches because they're so big and so many vertices are in them. Of course, there are ways to minimize these effects. But in general, we see that, for example, vegetation can be at play here and make results not as well as we would like them to be. So can we use deep learning to directly classify those point clouds? So to go from X, Y, Z, maybe accompanied by intensity or other things we have in the point cloud to a classified point cloud. And this classified point cloud, we could use this directly instead of a multi-patch in some cases, or create multi-patches from them. And well, in the last few years, a lot of deep learning frameworks specified on point clouds developed and are also integrated in ArcGIS. So I have some examples from PointCNN. And in this example, we see the traditional classified building points tool at the top and PointCNN at the bottom. And that one is better. If you look into detail, you can see that. Along with buildings, we can, of course, classify more things in the point cloud, and we can build a 3D map or a preliminary 3D map, I would say. And very nice to see here that in our training samples, we didn't have a windmill. It was just buildings. But the PointCNN model we trained was able to classify it as a building, which is really amazing. And here we see a difference between the old traditional way with a lot of extra noise and using PointCNN instead of it. Well, everything depends on the training of your point clouds, of course. So you have to train the deep learning model, and it has to learn how a tree looks like, what the intensity is, what the composition of the points should be. And this is the most of work. So we provide a lot of pre-trained deep learning packages in ArcGIS Online, which you can use directly or download and use them on your own data. It's not always that your data exactly suits on the model, because the model is trained on data we have. But in every case, it's better to use this one as a starting point, because you can retrain it with your own data as well. And then you don't have to do all the training. And it's maybe only 10% to refine the model to your own needs. And in this, here we have trees and power lines and power and poles of the power lines. And here we see an example. At the left, it is created by humans, classified by humans. At the right, by this model. And you see that the model was not very good here, because part of the vegetation, where also I think a adventure park thing was with some other lines, was also classified by the model as power lines. So that's not, it doesn't work always that good. So sometimes we have to retrain it. But in some cases, it's the other way around, because at the left side, we see some poles points classified as poles by human beings, which was actually wrong, because it were transformators. And at the right side, we see that the model did a better job. So the model is not always right, but it is very consistent. And humans are not so consistent. Then something very different from this is that this year, Azure will introduce ArcGIS Reality. Actually, that will be communicated in 2 weeks or so. But I checked it and I was allowed to tell you about this already. And with ArcGIS Reality, it is possible to use images, mostly from drones or aerial, to create the products you see at the right side. So those images must contain a lot of overlap, and this overlap can be used to create 3D point clouds, and the other products you see here. And of course, those images need orientations. With drone mapping, usually those orientations are embedded in the EXIF of those images, but it's also possible to have them separate to have more traction on what will happen. Yeah, within ArcGIS Reality, different products will come into play. ArcGIS Reality Studio will be a product where you can scale this up to a server cluster or multiple computers, for example, but there will also be an extension inside ArcGIS Pro alongside with our already existing drone mapping solutions. But why am I telling all this here? Because I think you already knew that some 3D point clouds can be derived from photogrammetry. That is, and this is an example of what you can create from those images. It is also an option to use LiDAR in this process at the left side. So usually if you don't use LiDAR, aerial triangulation is used to compute the tie points of the images. And from there, we can compute a parallax value for every pixel. And this is very processing intensive, so you need a lot of compute for this. And also, it is an estimation. So it is an estimation of the depth of the depths in every image. LiDAR can be very useful here because LiDAR doesn't have, isn't bothered by, for example, changes in shadow or things like this, which can disturb the process of aerial triangulation. So we can use, not yet, but later this year, it will come in the order I put these products in. LiDAR will be an option in all those products in the over time. And this may improve the accuracy a lot. And also the compute time we expect to drop because it is easier to get the right depths in the images. Well, that's what I wanted to tell today.
Thanks, William. Any questions? Of the SB developments? That's what?
Not really a question, but only a kind of a remark. I really like that your example, you showed the wind map, the windmill. Do you know the type of windmill?
No, I don't know exactly. No.
I just asked him the ChatGPT what kind of windmill we may have over here, and we have several. But I think these.
Yeah, but it is an old one, as you can see. So,
I really would have the idea that only with a kind of postcard representation, you can ask someone who really knows into this field what kind of windmill is, then he or she can answer the question. If you use a kind of other kind of mesh like whatever kind of representation, it will completely this model still kind of weird building type.
Yeah.
So only by having this couple of set of phones over there, they can say it is more kind of
yeah, but that would be really nice to have as a next step, that we can not only detect that this is a building, but that we can detect that this is a windmill from this type and stuff like that. But this this is all open for us now. Yeah.
Yes, about the integration with photogrammetry and LiDAR. How much of these two should be aligned while acquiring the data? Should the LiDAR be at the same location as the camera, more or less? When you acquire the data, can it be done completely afterwards with no correlation between acquisition dates?
No, that right now there must be correlation. So you need, if you want to use it, at least for now, I don't know what the future brings, but for now, you need to acquire it at the same time as that you acquire the imagery. For example, the vibration of the plane is very important. That you know that it is taken from exactly that location. So that there are also from, I think, Leica Geosystems cameras which have both of them. This is best. It can be separate, but it must be done in one flight. Yeah.
About the machine learning, that's very interesting. So which neural network, say, is preferred in your opinion? You showed several of them,
yes,
and others. And so which one is kind of the default in the S3 stack?
Oh, that's a good question. I don't know really, but I know that for PointClouds, it is only, there are only a few like PointNet and PointCNN that I showed, but I don't know really. We don't really have one official preference, I think. But for the raster detection, mask, RCNN, I see a lot of them, but also YOLO, for example.
Yeah.
So I actually I don't know really.
Depends on the user, on what the data.
It's sometimes it also depends a little bit on what you want to get as output. Yes.
And the training data, that's very important. How do you get the training data, or how does Esri get the training data? By manual labeling?
Yes, and this is a lot
of work.
Yes.
I remember that Marcus was working on editing tools to lasso a cluster of points, and then say, okay, this is windmill, this is building 1, this is street 3. So interactive editing tool could help to create training data.
Yeah,
but then you still need to make mistakes.
Yeah, and labeling only 5 windmills is not enough. So you need really 100 or more of them. So yeah.
Any more questions? Let's continue. William, next one. Yes.
Thanks for being here.
Okay, it has been a very long day, a lot of presentations, a lot of content, but okay, this is maybe the only one with no real content. Because this is more an overview of the things that we have been doing and some reflection. So I think we have some good foundations. We looked at some use cases. We developed software, initial software. We explored different hardware tools, which was also very nice. And we made a number of publications, and I hope Haicheng is still awake in China, but he was the first publication is his thesis. That was his end of the career at the university, but it was also kind of the start of our project coinciding. And then we have, say, the follow-up on convex polytope queries and the continuous level of importance of detail. This was in the project plan. And we have a number of work packages. Okay, work package 1 is kind of the organization, communication, standardization, things like that. It's ongoing, but say the real work is in the package 2 until 6. So I would say our base model is the nD-PointClouds and the CLOI. We are there about 80%. Data management, we're still struggling with files, databases, compression, individual points, blocks, but making good progress, getting a feeling what does work. Then the high performance computing, high throughput computing, we made a good start. We are now getting a good grip on Delft Blue, trying to do massive conversions, also trying to do massive analysis, like change detections from AN or from the code scan data, and have different algorithms, or maybe also coordinate transformations from local coordinates into georeference coordinates. Visualization, we had a bit of a false start. We did something, but not that much. I'll explain you later why. It also makes sense. It was planned a bit more at the end. And yeah, we still also have to get a good start with the proof of concept after the preparations. I would say it was not an easy start. About a little bit more than a year ago, we were also in this room and we were thinking, okay, nice kickoff. And then suddenly COVID came back again quite hard. E-science people were, for example, not allowed to travel anymore. And that was true for some other people. So we were about 50-50 on site, on location. Okay, in spring it got better, we thought. So we planned Marcus Schutz visits to Delft in the week of 21 March. But some of the TU Delft staff, including myself, got COVID the week before. Marcus came, was fit, and talked to the other fit people. By the way, I did never feel that I had COVID, but the test showed, and yeah, I had to stay at home. Unfortunately, Marcus also got infected during his visit in Delft, and he had to stay longer in the Netherlands. Sorry, Marcus, before he could travel back to Austria.
Oh, no problem. I don't think that was actually because of COVID in Netherlands, maybe just a common cold that hit me. The
Okay.
tests were all negative.
Okay, maybe that's too negative. In the visualization, Maarten van Meersbergen started to work on the Poetry viewer, and including CLOI. But he chose to go for another job or another research job, so he has left. And I was also away for a while, which was my sabbatical for 5 months. I was in Scandinavia, Sweden, which is not good. Vitaly had a quite a tough learning curve, coming from more the raster world, and now getting into the point cloud world. He was used to spatial temporal stuff. But still, on the bright side, I think we have good ideas on how to create these conversions efficiently, to have a multi-dimensional organization in different environments. Martijn Thijs worked on that. Vitaly has explored and cleaned some interesting spatial temporal data sets. That is really very interesting to see these time series, also high resolution time series. We asked the Delft Digital Competence Center for support, and we got it. So Manuel Garcia helped us a lot previous year during the project to get started with Delft Blue. Naumann joined, as you saw in the presentation. We got some new hardware. Edward already showed something, and we are now trying to get our own successor of Pakhuis, which is our own big machine. And that looks really good. So hopefully quite soon we have a nice machine. And the main thing is it has a lot of SSD. So it has also 48 cores. Good normal disk, quite a bit of main memory, but especially we're now focusing on SSD to see how fast we can get with that. I think Martijn was about 16 terabyte SSD or something like that. So different types of SSD also, with good meetings. And as Edward showed, quite a number of students worked on point cloud related projects. So looking ahead, what to do? Okay, we had now a workshop, more presentations and discussion. And I was thinking maybe we should have a meeting more often. Depends also if you think that is useful. So maybe 2 times per year or 3 times per year. Then have some presentations and the other half discussion. So longer discussion after the presentation. I think it's also good if we are more active in standardization. For example, the OJC to have point clouds being standardized on the web, and then there is always a tension between the standard, say more or less 3D point clouds, maybe with RGB, and if you want to go n-dimensional, just having time and level of detail. What is a good generic standard, which is not too complicated to implement? And we have this infrastructure plan. So now we focus mainly on the point cloud basis and the point cloud base, but we should move to the open point cloud infrastructure where we work with different skills like the ZEP Horizon and the Coast Scan and AHN and try to put them together. So we have to figure out how to work the coordinate reference systems to do the transformations. These datasets have different attributes, really physical attributes, different densities, different moments in time, update times. They are maybe hosted on different services. So you have to agree on the protocols, and maybe you want to use different clients. So I think we should try to promote our ideas, get support from industry, from other researchers, put forward suggestions for standard protocols, formats. Try also to get CLOI aware viewers. The initial start has been shown by Thijs. We should continue with it. And then we have some open questions. So if we do coordinate transformations of a data set, because the client is working in the data set, but on the server side or in the capturing, it is in other coordinate references. And what do we do? Do we do it on the fly of the selection? So a client is selecting a set of data in his area of interest and then do fast conversion on the fly? Or do we pre-compute the most used coordinate reference system and store them redundantly, which can be expensive with so much data? Can we use CLOI to integrate data sets at different scales after correct georeferencing and coordinate transformations? And about change detection, and also the movie that was shown from the Coast Scan data for the animation is also something I have in mind, but then being able to also zoom in, rotate, look at from all sides and go back in time and forward. So in discussions, we were thinking, should we add one dimension to every point, one attribute added to every point, and that is the change to the previous moment in time, the previous epoch. And then you can visualize it very quickly. You can also maybe do animations very quickly with color coding. And you can compute quantities of change. So is one additional attribute enough to do this fast visualization analysis, or is it more complicated? That was it. Let's have a bit of discussion about, okay, should we, or would you, if I invite you, say after a couple of months again for a workshop, would you find it interesting? Or would you say once per year is enough? It's an open question. I think I would go for 2 times per year. So have one more meeting, say after the summer break, which is then already a doubling in the frequency. Any thoughts? Sounds good. Okay. Any other hot topics? Okay, we have seen different future works, and here there are more future works. I think maybe the best thing now is go for a drink and a snack. And I would like to thank you for being here and listening. I try to capture everything on the video, disseminate it after the meeting, and also the presentations. Thanks for your time, and see you at the other side near the drinks. Goodbye, everybody online.